Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient journey of Comet 3 I/Atlas, a wanderer that carries within its frozen heart the memory of stellar birth and death across unimaginable spans of time. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the cold vastness between stars, where darkness stretches for light years in every direction, something stirs. Not life, not consciousness, but movement nonetheless. A slow drift through the cosmic void that has continued for millions upon millions of years. Here, in this realm where temperatures hover just above absolute zero, where the nearest star appears as nothing more than a distant point of light, Comet 3 I/Atlas begins its story. Though it bears a name given by human astronomers in the early 21st century, its existence spans epochs that dwarf the entire history of human civilization. The comet moves through space at 17 kilometers per second relative to our Sun, a velocity that seems impossibly fast until one considers the scale of interstellar distances. At this speed, crossing the gap between Earth and Moon would take less than 6 hours. Yet the journey from its birthplace among distant stars to our solar system has required geological ages. Time flows differently in the spaces between worlds, measured not in human lifespans or even in the rise and fall of species, but in the slow waltz of stellar orbits around the galactic center. What emerges from the darkness carries within its nucleus the chemical signature of its origin, a fingerprint written in isotopes of carbon, nitrogen, and oxygen that speaks of processes occurring in the heart of dying stars. The comet's core, perhaps 2 kilometers across, consists of materials that condensed from stellar winds when our galaxy was younger and contained fewer heavy elements. These ancient ices and organic compounds survived the violent birth of new star systems, the supernova explosions that scattered heavy elements across space, and countless encounters with cosmic radiation that might have altered their composition. The scientific mystery deepens when astronomers examine the comet's trajectory and realize that its path through space shows no obvious gravitational perturbations from nearby stellar systems. Unlike many interstellar visitors that bear the clear gravitational fingerprints of their encounters with other stars, 3 I/Atlas appears to have wandered through the galaxy's spiral arms with remarkable isolation. This suggests either an origin in the sparse regions between spiral arms, where stellar densities remain low, or a journey so ancient that the gravitational influences that initially set it in motion have been erased by time and distance. Only took 4.5 billion years to make this appointment with our Sun. The irony lingers in the mathematical precision of celestial mechanics, how random motion through space can appear so purposeful when viewed from the perspective of a single solar system. The comet's approach vector suggests it has never visited our neighborhood before, yet its trajectory aligns so perfectly with the plane of planetary orbits that it seems almost deliberate. Another quiet irony emerges from the realization that this ancient wanderer, older than the Earth itself, will spend mere months in our vicinity before continuing its journey toward destinations unknown. The third irony rests in the comet's composition, which preserves materials from the early solar system more perfectly than any object that remained gravitationally bound to our Sun. While the planets and asteroids of our system have been repeatedly heated, melted, and chemically altered by 4.5 billion years of solar radiation and internal processes, This interstellar visitor carries pristine samples of the molecular cloud from which our solar system condensed. As 3I/Atlas drifts through the outer reaches of our solar system, still beyond the orbit of Neptune, it remains essentially inert. No tail streams behind it, no coma of sublimating gases surrounds its nucleus, in the bitter cold of deep space, where sunlight provides less warmth than a candle flame viewed from across a football field. The comet's ancient ices remain locked in solid form. Water molecules that condensed from stellar atmospheres billions of years ago maintain their crystalline structure, while organic compounds that predate the formation of Earth wait in frozen suspension. The comet's surface tells a story written in impacts and sublimation over cosmic time. Microscopic meteoroid strikes have sandblasted its exterior for millions of years, creating a dark, porous layer that insulates the pristine interior from the minimal heat of distant stars. This protective mantle, composed of organic compounds and silicate dust, gives the comet's nucleus an albedo, a reflectivity darker than charcoal. Yet beneath this protective coating, the original materials remain largely unchanged, a library of cosmic history preserved in ice and dust. Gravitational forces begin their subtle work even at these vast distances. The sun's influence, while weak at the edge of the solar system, still exceeds that of any other nearby star. The comet's hyperbolic trajectory, a path that would normally carry it through our system once and then back to interstellar space, begins to bend ever so slightly inward. This gravitational focusing effect, predicted by Newton's laws and confirmed by Einstein's general relativity, will determine whether 3I/Atlas becomes a temporary visitor or finds itself captured into a long-term orbital relationship with our star. The mathematics of orbital mechanics operate with the same inexorable precision that governs the motion of planets and the oscillation of pendulums. As the comet approaches, its kinetic energy and potential energy exchange in a cosmic dance that will determine its ultimate fate. If its velocity remains too high, it will sweep through the inner solar system once and escape forever. If stellar encounters or planetary perturbations reduce its speed sufficiently, it might join the population of long-period comets that return to visit our sun every few thousand years. Modern analogy emerges in the similarity between the comet's journey and the path of a paper airplane thrown into a gentle breeze. Just as air currents can alter the plane's intended trajectory in subtle but significant ways, the gravitational currents of space, created by the sun, planets, and even the galaxy itself, guide the comet's motion through three-dimensional space. Unlike the paper airplane, however, the comet's flight continues for millions of years, and the breeze consists of invisible gravitational fields that extend across light years. In the darkness beyond Neptune's orbit, 3I/Atlas continues its ancient pilgrimage toward the inner solar system, carrying within its frozen heart the chemical memory of stellar birth and death. Each molecule of water ice, each grain of cosmic dust, each complex organic compound tells part of a story that began when the universe was younger and the Milky Way contained fewer of the heavy elements that make planets and life possible. The comet approaches not as a harbinger of doom or a messenger of the gods, but as a time capsule from the deep past, offering scientists a glimpse into the conditions that prevailed when our solar system was still forming. Time moves differently in the realm of comets, measured not in human heartbeats or seasonal cycles, but in the slow accumulation of gravitational influences and the patient sublimation of ancient ices. As 3I/Atlas continues its journey inward, it carries with it the quiet mysteries of interstellar space and the promise of revelations about the cosmic processes that shaped our corner of the galaxy. Its path was chosen not by conscious intention, but by the mathematical poetry of gravitational mechanics operating across scales of space and time that challenge human comprehension. The invisible architecture of space reveals itself through motion. Around Comet 3 I/Atlas, gravitational fields extend like unseen rivers flowing through the void, each carrying the mathematical signature of distant massive objects. These currents have no substance that human senses could detect, no temperature, no texture, no resistance to passage. Yet they possess the power to bend the trajectory of worlds. The comet drifts through this invisible landscape like a leaf carried by streams that flow not with water, but with the curvature of space-time itself. Einstein's general relativity describes gravity not as a force pulling objects together, but as the warping of the fabric of space and time by mass and energy, near massive objects like stars. This warping becomes pronounced, creating steep gravitational wells that trap planets in orbital motion. In the spaces between stars, the curvature remains gentle but persistent, creating subtle gradients that can accumulate over millions of years to produce dramatic changes in trajectory. The comet has navigated these gravitational currents for eons, its path shaped by stellar encounters so distant and ancient that their origins have been lost to time. Every star within 50 light-years of 3 I/Atlas's current position contributes its own gravitational whisper to the cosmic chorus that guides the comet's motion. Proxima Centauri, our nearest stellar neighbor, exerts a gravitational pull so minute that it would require sensitive instruments to detect its influence. Yet over the millions of years of the comet's journey, even this faint tug has contributed to the subtle adjustments in trajectory that brought the ancient wanderer toward our solar system. The red dwarf, Barnard's star. The white dwarf, Sirius B, the binary system of Alpha Centauri. Each adds its voice to the gravitational symphony that has choreographed the comet's approach across interstellar distances. The mathematics describing these gravitational interactions operate simultaneously across multiple scales of space and time. On the largest scale, the Milky Way galaxy itself creates a background gravitational field that influences the motion of all objects within it, including our solar system and any visitors from interstellar space. The galaxy's spiral arms, dense with stars and gas clouds, create regions of enhanced gravitational complexity where stellar encounters become more frequent. Between the spiral arms, in the quieter regions where our solar system currently resides, gravitational influences remain more subtle but no less significant in their cumulative effects. As 3 I/Atlas approaches the boundary of our solar system, it enters a region where the Sun's gravitational influence begins to dominate over that of nearby stars. This transition occurs gradually across a zone millions of kilometers wide, where competing gravitational fields create complex tidal effects. The boundary itself, known as the Hill sphere, defines the region within which our Sun's gravity can maintain long-term control over orbiting objects despite the competing influences of other stars and the galaxy as a whole. For our solar system, this sphere of gravitational dominance extends roughly 2 light-years in all directions, encompassing the hypothetical Oort cloud and creating a vast 3-dimensional territory within which the Sun rules supreme. The comet's nucleus, though small compared to planets or moons, still experiences differential gravitational forces across its diameter. These tidal stresses remain far too weak to disrupt the comet's structure, but they serve as harbingers of the more dramatic forces it will encounter as it approaches the inner solar system. The same tidal effects that raise ocean waters on Earth and gradually slow the moon's rotation operate on much smaller scales throughout the solar system, creating subtle distortions in the shape and internal structure of all orbiting bodies. Within the solar system's gravitational architecture, the giant planets serve as gravitational shepherds, their massive presence creating zones of orbital stability and instability that determine the long-term fate of smaller objects. Jupiter, with a mass greater than all other planets combined, acts as the solar system's primary gravitational organizer, clearing debris from certain orbital regions while concentrating it in others. The asteroid belt between Mars and Jupiter represents one such zone of gravitational organization, where resonances with Jupiter's orbital period prevent the formation of a single large planet while maintaining a stable population of smaller rocky bodies. The scientific mystery of 3I/Atlas's precise origin deepens when astronomers attempt to trace its trajectory backward through time. Computer models can extrapolate the comet's path into the past with remarkable precision for hundreds or even thousands of years, accounting for the gravitational influences of known objects within our solar system. But extending this backward projection across the millions of years required to reach its presumed stellar birthplace introduces cumulative uncertainties that grow exponentially. Small measurement errors in the comet's current position and velocity propagate backward through time, creating cone-shaped regions of uncertainty that eventually encompass multiple star systems. This computational challenge illustrates a fundamental limitation in predicting the behavior of chaotic systems over long timescales. While the gravitational interactions governing the comet's motion follow deterministic physical laws, the extreme sensitivity of orbital trajectories to initial conditions means that tiny uncertainties in measurement inevitably lead to large uncertainties in long-term predictions. The same mathematical principles that make weather forecasting impossible beyond a few weeks make it equally challenging to trace comet trajectories across geological time periods with absolute precision. Only took several million years for gravity to write this invitation in the language of orbital mechanics. The comet's approach to our solar system appears almost serendipitous, a chance encounter between an ancient wanderer and our gravitationally bound family of worlds. Yet the mathematics governing this encounter operate with the same deterministic precision that governs the motion of clockwork, suggesting that what appears random may simply reflect the complexity of a system with too many variables for human minds to fully comprehend. The irony persists in the way chaos theory applies to celestial mechanics, predictable physical laws governing the motion of objects whose long-term behavior remains fundamentally unpredictable. Another irony emerges from the comet's relationship to time itself. While 3I/Atlas carries materials that predate our solar system, its current trajectory was established relatively recently in cosmic terms, perhaps only a few million years ago when a close encounter with a distant star provided the gravitational nudge that sent it in our direction. The comet thus represents both ancient materials and relatively recent motion, a messenger from the deep past carrying news delivered by comparatively modern gravitational mail. This temporal paradox reflects the complex relationship between the age of objects in space and the age of their current orbital configurations. The third ironic observation lies in the precision with which invisible forces have guided the comet's journey. Gravitational fields that cannot be seen, heard, touched, or directly measured have nonetheless carved the comet's path through space with mathematical exactitude. These unseen rivers of curved space-time have operated as a kind of cosmic GPS system, guiding the comet across interstellar distances toward an appointment with our Sun that was scheduled by the laws of physics rather than any conscious intelligence. The comet's motion through these gravitational currents creates no wake, produces no friction, generates no heat. Unlike objects moving through material media like air or water, celestial bodies in vacuum experience no resistance to their motion. This absence of drag means that once set in motion, the comet will continue its journey indefinitely unless acted upon by external forces. The same principle that allows planets to maintain their orbits for billions of years permits comets to cross interstellar space without losing momentum, their kinetic energy preserved across spans of time that encompass the evolution of entire stellar systems. As 3I/Atlas continues its approach, the Sun's gravitational field begins to accelerate the comet noticeably. This acceleration follows the inverse square law, meaning that gravitational force increases dramatically as distance decreases. At the comet's current position, perhaps 50 astronomical units from the Sun, solar gravity exerts only a gentle tug. But this seemingly modest force, acting continuously over months and years, will eventually increase the comet's velocity by several kilometers per second, enough to significantly alter its trajectory and determine whether it will escape back to interstellar space or remain gravitationally bound to our solar system. The gravitational dance between comet and star occurs according to conservation laws that govern all motion in the universe. As the comet falls deeper into the Sun's gravitational well, it trades potential energy for kinetic energy in a cosmic analog to a ball rolling down a hill. This energy exchange follows mathematical relationships discovered by Kepler, Newton, and Einstein. Equations that describe motion from the scale of falling apples to the orbital mechanics of galaxies. The total energy of the comet-Sun system remains constant throughout this process, redistributed between kinetic and potential forms, but never created or destroyed. Stellar astronomers studying 3I/Atlas face the challenge of measuring gravitational effects too subtle for direct detection. The comet's change in velocity due to solar gravity amounts to mere meters per second over periods of weeks, changes detectable only through precise measurements of the comet's position against the background stars. These observations require the most sensitive instruments available to ground-based and space-based telescopes, capable of detecting angular movements smaller than the apparent diameter of a coin viewed from several kilometers away. The accumulated measurements, taken over months or years, reveal the comet's gradually changing trajectory with remarkable precision. Like a river delta where multiple streams converge and diverge, the gravitational environment around our solar system creates complex current patterns that can redirect incoming objects in unexpected directions. The comet navigates these currents with the passive grace of a sailing ship carried by winds it cannot control, its ultimate destination determined by the mathematical interplay between its initial velocity and the gravitational forces it encounters along the way. Beyond the orbit of Pluto, where sunlight arrives as little more than starlight and temperatures hover near absolute zero, Neptune's gravitational presence extends like a cosmic lighthouse beacon. Though the ice giant appears as merely a pale blue dot when viewed from this distance, its gravitational field reaches far beyond its visible boundaries, creating the first significant planetary perturbation that Comet 3I/Atlas will encounter in its approach to the inner solar system. This distant greeting occurs across millions of kilometers of empty space, a handshake between worlds conducted entirely through the invisible medium of curved space-time. Neptune orbits the Sun at an average distance of 30 astronomical units, requiring nearly 165 Earth years to complete a single orbit. From the comet's current position, still approaching from the outer reaches of the solar system, Neptune represents the outermost sentinel of planetary influence. The ice giant's mass, 17 times that of Earth, creates gravitational effects that extend well beyond its immediate vicinity, reaching out to influence the motion of objects in the Kuiper belt and occasionally redirecting long-period comets onto trajectories that bring them closer to the Sun. The gravitational interaction between Neptune and the approaching comet operates according to principles first described by Newton's law of universal gravitation, later refined by Einstein's general relativity. As 3I/Atlas approaches Neptune's sphere of influence, the ice giant's gravity begins to compete with the Sun's gravitational pull, creating a complex three-body problem that defies simple analytical solutions. The comet's trajectory, which appeared straightforward when viewed from a distance, now begins to curve in response to Neptune's gravitational field, its path bending like light passing through a cosmic lens. This gravitational deflection occurs so gradually that human observers would notice no immediate change in the comet's apparent motion against the background stars. Yet, over the course of weeks and months, Neptune's influence accumulates, subtly altering the comet's velocity vector by tiny amounts that will have profound consequences for its ultimate trajectory through the solar system. The ice giant acts as a gravitational slingshot, either accelerating or decelerating the comet depending on the geometry of their encounter, potentially changing 3I/Atlas from a hyperbolic visitor destined to escape the solar system into an elliptical captive bound to return in future millennia. The mathematical precision of this gravitational interaction reflects the fundamental conservation laws that govern all motion in the universe. As the comet approaches Neptune, the total angular momentum and energy of the comet-planet-sun system remain constant, redistributed among the various components but never created or destroyed. This conservation principle ensures that Neptune's gravitational assistance comes at a cost. The ice giant's own orbital energy decreases by an infinitesimal amount as it accelerates the comet, though this change remains far too small to affect Neptune's motion in any measurable way. Neptune's discovery in 1846 represents one of the greatest triumphs of theoretical astronomy. The planet's existence and location predicted through mathematical analysis of gravitational perturbations in Uranus's orbit before any telescope had glimpsed its azure disk. The same gravitational mathematics that revealed Neptune's presence now govern its interaction with Comet 3I/Atlas, demonstrating the universal applicability of physical laws across scales ranging from laboratory experiments to planetary motions. The equations describing the gravitational force between any two masses apply equally to falling apples, orbiting planets, and wandering comets approaching from interstellar space. The scientific mystery surrounding Neptune's precise influence on the comet's trajectory lies in the complex interplay between multiple gravitational sources operating simultaneously. While astronomers can calculate Neptune's gravitational effect on 3I/Atlas with high precision, the cumulative influence of other objects, Uranus, Saturn, Jupiter, and even the larger asteroids, creates a many-body problem that requires sophisticated computer models to solve. Small uncertainties in the masses and positions of these various objects propagate through the calculations, introducing minute but potentially significant errors in predicting the comet's future path. Only took 4.5 billion years for Neptune to reach the perfect position for this cosmic encounter. The irony emerges from the apparent coincidence that brings comet and planet into gravitational contact at precisely this moment in cosmic history. Neptune's orbital period means that its current position along its elliptical path occurs only once every century and a half. Yet the comet's million-year journey through interstellar space has timed its arrival to coincide with this particular configuration of planetary positions. The mathematical probability of such precise timing appears vanishingly small, yet the vast scales of space and time ensure that seemingly improbable encounters occur with statistical regularity. Another ironic observation concerns the relationship between Neptune's discovery and its role in redirecting interstellar visitors. The ice giant remained hidden from human awareness for all but the most recent centuries of our species' existence, its presence known only through its gravitational effects on neighboring worlds. Yet Neptune has been quietly shepherding comets, asteroids, and other small bodies throughout the solar system's history, its gravitational influence shaping the architecture of the outer solar system long before humans evolved the mathematical tools to understand its effects. The planet's role as a cosmic traffic director predates its discovery by billions of years. The third irony lies in the delicate balance between order and chaos that Neptune's gravitational influence represents. While the ice giant's gravity operates according to perfectly deterministic physical laws, its interaction with the comet introduces an element of chaotic dynamics that makes long-term predictions increasingly uncertain. The same gravitational force that maintains Neptune's stable orbit around the Sun creates instabilities in the trajectories of smaller objects, ensuring that the solar system's population of comets, asteroids, and meteoroids remains in constant flux over geological timescales. Neptune's atmosphere, composed primarily of hydrogen and helium with traces of methane that give the planet its characteristic blue color, rotates faster than the planet itself, creating winds that reach speeds of over 2,000 kilometers per hour. These atmospheric dynamics, driven by heat from the planet's interior rather than solar radiation, create weather patterns that persist for decades or centuries. Yet despite the violence of Neptune's atmospheric storms, the planet's gravitational field remains perfectly smooth and predictable, extending uniformly in all directions according to the inverse square law that governs all gravitational interactions. The ice giant's magnetic field, generated by convection currents in its water-ammonia mantle, creates a protective magnetosphere that deflects charged particles from the solar wind. This magnetic environment extends far beyond Neptune's atmosphere, creating a complex three-dimensional structure that can trap cosmic rays and particles from interstellar space. As Comet 3 I/Atlas passes through this magnetic environment, any charged particles or plasma surrounding the comet's nucleus may interact with Neptune's magnetic field, creating subtle electromagnetic effects that complement the dominant gravitational interaction. Telescopic observations of the comet during its encounter with Neptune's gravitational field provide astronomers with valuable information about both objects. By precisely measuring the comet's trajectory before, during, and after its closest approach to Neptune, scientists can refine their understanding of the ice giant's mass and gravitational field. Conversely, Neptune's well-known gravitational properties allow astronomers to use the planet as a cosmic scale, weighing the comet's mass through careful analysis of how strongly it responds to Neptune's gravitational pull. The encounter between 3 I/Atlas and Neptune represents a fleeting moment in both objects' long histories. For the comet, this gravitational interaction may determine whether it will escape the solar system forever or remain bound to orbit the Sun for millions of years to come. For Neptune, the comet's passage represents an insignificant perturbation, one of countless small bodies that have passed through the ice giant's sphere of influence over the past 4.5 billion years. Yet this brief cosmic encounter, lasting only months from beginning to end, illustrates the interconnected nature of celestial mechanics and the profound influence that distant objects can exert on one another through the universal force of gravitation. As the comet continues its journey deeper into the solar system, Neptune's gravitational farewell gradually diminishes, its influence yielding to the stronger pull of the Sun and the gravitational presence of the inner planets. The ice giant returns to its patient orbit, its role in the comet's story complete but not forgotten. Encoded forever in the subtle changes to 3 I/Atlas's velocity and trajectory that will influence its motion for the remainder of its cosmic journey. In the gravitational hierarchy of our solar system, Jupiter reigns supreme among the planets, a gas giant whose mass exceeds that of all other planets combined by a factor of more than 2. As Comet 3 I/Atlas continues its inward journey, having received Neptune's distant gravitational greeting, it now approaches the sphere of influence of this cosmic colossus. Jupiter's gravitational reach extends far beyond its visible disk, creating a zone of influence that stretches across hundreds of millions of kilometers of space. Within this vast domain, the King of Planets exercises absolute authority over the trajectories of smaller objects, determining their ultimate fate with the inexorable precision of celestial mechanics. Jupiter orbits the Sun at an average distance of 5.2 astronomical units, completing its majestic circuit once every 11 Earth years and 315 days. From this position in the middle regions of the solar system, the gas giant serves as both protector and destroyer, its gravitational field acting as a cosmic vacuum cleaner that sweeps up potentially dangerous asteroids and comets before they can threaten the inner planets. Yet this same gravitational influence can also accelerate objects to escape velocity, flinging them out of the solar system entirely or redirecting them onto collision courses with other worlds. For Comet 3 I/Atlas, the encounter with Jupiter represents the most critical moment in its entire journey through our solar system. The physics governing Jupiter's gravitational interaction with the approaching comet follow the same fundamental laws that describe all motion in the universe. Yet, the complexity of the three-body problem involving the comet, Jupiter and the Sun, defies simple analytical solutions. As 3I/Atlas approaches Jupiter's Hill sphere, the region within which the planet's gravity dominates over solar influence, the comet's trajectory begins to bend according to hyperbolic geometry. The precise curvature of this path depends on the comet's approach velocity, its closest distance to Jupiter, and the angle at which it encounters the gas giant's gravitational field. The gravitational slingshot effect that Jupiter can provide operates through the conservation of energy and momentum in the reference frame of the planet itself. As the comet approaches Jupiter, it accelerates under the influence of the gas giant's gravity, gaining kinetic energy as it falls deeper into Jupiter's gravitational well. At the moment of closest approach, the comet reaches its maximum velocity relative to Jupiter before beginning to decelerate as it climbs back out of the gravitational well. In Jupiter's reference frame, the comet's speed remains unchanged by this encounter, entering and leaving with identical velocities. However, in the Sun's reference frame, Jupiter's own orbital motion around the Sun creates an asymmetry that can dramatically alter the comet's heliocentric velocity. The mathematical beauty of this gravitational choreography emerges from the vector addition of velocities in different reference frames. If the comet approaches Jupiter from behind in the planet's orbit, it can gain significant velocity in the direction of Jupiter's motion around the Sun, potentially increasing its heliocentric speed by several kilometers per second. Conversely, a head-on encounter can decelerate the comet relative to the Sun, potentially reducing its velocity below the escape threshold and trapping it in a long-period elliptical orbit. The geometry of this encounter, determined by cosmic coincidence and the accumulated gravitational influences of the comet's long journey, will decide whether 3I/Atlas becomes a permanent resident of our solar system or continues its voyage back to interstellar space. Jupiter's massive presence has shaped the architecture of the entire solar system through billions of years of gravitational influence. The gas giant's formation early in the solar system's history prevented the accumulation of material between Mars and Jupiter, creating the asteroid belt as a population of planetary building blocks that never coalesced into a single world. The Trojan asteroids, trapped in Jupiter's orbit at gravitational equilibrium 0.60 degrees ahead of and behind the planet, demonstrate the gas giant's ability to capture and hold smaller objects in stable configurations. The complex family of Jovian moons, from the 4 Galilean satellites to dozens of smaller captured asteroids, further illustrates Jupiter's role as a gravitational organizer of the solar system. The scientific mystery surrounding Jupiter's precise effect on Comet 3 I/Atlas lies in the challenge of measuring and modeling all the factors that influence the gravitational encounter. While Jupiter's mass and orbital parameters are known with high precision, small uncertainties in the comet's exact position, velocity, and physical properties propagate through the calculations to create meaningful uncertainty in predicting the encounter's outcome. The influence of Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, adds additional complexity to the gravitational environment. Their combined mass representing nearly 1% of Jupiter's total and creating subtle perturbations that can affect the trajectories of passing objects. The challenge becomes even more complex when considering Jupiter's oblate shape, caused by the planet's rapid rotation period of less than 10 hours. This rotational flattening creates a gravitational field that deviates slightly from the perfect sphere assumed in simplified calculations, introducing higher-order terms in the gravitational potential that can influence the motion of nearby objects. For most purposes, these deviations remain negligible. But for precise trajectory calculations involving close approaches to the gas giant, they become significant factors in determining the comet's ultimate path. Only took 4.5 billion years for Jupiter to position itself as the solar system's gravitational gatekeeper. The irony emerges from the gas giant's dual role as both protector and destroyer of smaller objects. The same gravitational field that has shielded the inner planets from bombardment by asteroids and comets over geological time also possesses the power to eject objects from the solar system entirely, banishing them to the cold emptiness of interstellar space. Jupiter's protection comes at the cost of exile for many visitors, a cosmic immigration policy that maintains stability through exclusion. Another ironic aspect of Jupiter's gravitational dominance lies in the relationship between the planet's immense size and its gaseous composition. Despite containing more mass than all other planets combined, Jupiter lacks a solid surface on which spacecraft could land or from which material could be easily collected. The gas giant's gravitational field, so powerful that it can alter the trajectories of objects millions of kilometers away, arises from matter so diffuse that a human could fall through Jupiter's upper atmosphere for hours before encountering material dense enough to provide significant resistance. The planet's gravitational authority extends across vast regions of space, yet Jupiter itself remains largely empty space, punctuated by gradually increasing densities of hydrogen and helium. The third irony concerns the precision with which Jupiter's gravitational influence operates despite the chaotic nature of multi-body dynamics. While the mathematical equations governing the comet's interaction with Jupiter follow deterministic physical laws, small changes in initial conditions can lead to dramatically different outcomes over time. This sensitivity to initial conditions, a hallmark of chaotic systems, means that tiny measurement uncertainties in the comet's current trajectory translate into large uncertainties in predicting its post-encounter path. The same gravitational forces that operate with clockwork precision in two-body problems become sources of fundamental unpredictability when extended to more complex multi-body interactions. Jupiter's internal structure, hidden beneath its dense atmosphere, generates a powerful magnetic field that extends far beyond the planet's visible boundaries. This magnetosphere, fed by volcanic emissions from the Moon, Io, and shaped by the solar wind, creates a complex electromagnetic environment that can trap charged particles and cosmic rays. As Comet 3 I/Atlas passes through this magnetic domain, any ionized gases in its vicinity may interact with Jupiter's magnetic field, creating auroral displays in the gas giant's polar regions and contributing subtle electromagnetic forces to the gravitational dynamics of the encounter. The gas giant's atmospheric dynamics, driven by internal heat left over from the planet's formation, create a complex system of rotating storms and jet streams that persist for decades or centuries. The Great Red Spot, a hurricane-like storm larger than Earth that has raged for at least 300 years, demonstrates the long-term stability that can emerge from seemingly chaotic atmospheric processes. Yet despite the violence of Jupiter's weather systems, these atmospheric phenomena have no direct effect on the comet's trajectory, which responds only to the smooth, spherically symmetric gravitational field generated by the planet's mass distribution. Modern spacecraft missions to Jupiter have provided detailed measurements of the gas giant's gravitational field, revealing subtle variations that reflect the planet's internal structure and composition. The Juno mission, currently orbiting Jupiter in a highly elliptical trajectory, uses precise tracking of its orbital motion to map Jupiter's gravitational field with unprecedented accuracy. These measurements reveal that Jupiter's interior contains a partially dissolved core of rock and ice, surrounded by layers of metallic and molecular hydrogen that create the planet's powerful magnetic field and contribute to its complex gravitational environment. The encounter between Comet 3, Atlas, and Jupiter represents a natural experiment in celestial mechanics, providing astronomers with an opportunity to test their understanding of gravitational physics under extreme conditions. By carefully tracking the comet's trajectory before, during, and after its closest approach to Jupiter, scientists can verify theoretical predictions and refine their models of multi-body gravitational interactions. The comet serves as a test particle in Jupiter's gravitational field, its motion revealing details about the gas giant's mass distribution and gravitational environment that might otherwise remain hidden. As the comet approaches the critical moment of its encounter with Jupiter, the accumulated gravitational influences of its journey through the outer solar system converge to determine its ultimate fate. The subtle nudges provided by Neptune and the other outer planets, the precise timing of its arrival in Jupiter's vicinity, and the exact geometry of its approach vector all combine to influence the outcome of this cosmic collision course. Within the span of a few weeks or months, Jupiter's gravitational choreography will write the final chapter of the comet's relationship with our solar system, determining whether 3I/Atlas will join the population of periodic comets bound to return in future millennia or continue its ancient journey toward destinations among the stars. As Comet 3I/Atlas ventures deeper into the solar system, having navigated the gravitational gauntlet of the outer planets, it begins to experience the growing influence of our star, the Sun's voice, which whispered softly at the distant edges of the Kuiper Belt, now speaks with increasing authority as the comet crosses the orbit of Jupiter and enters the realm where solar radiation becomes a significant force. For the first time in its million-year journey through the cold darkness of interstellar space, the ancient wanderer begins to feel the warming touch of stellar energy, and its frozen surface starts to respond with the tentative stirrings of sublimation. The transformation begins gradually, almost imperceptibly, as solar photons strike the comet's dark nucleus with ever-increasing intensity. At distances beyond Jupiter's orbit, where 3I/Atlas now travels, sunlight arrives with roughly 4% of the intensity it provides to Earth. This seemingly modest level of illumination, equivalent to a heavily overcast day on our planet, nonetheless represents a dramatic increase from the nearly absolute cold that has preserved the comet's pristine materials for millions of years. The temperature of the nucleus begins its slow climb from near absolute zero toward the sublimation point of water ice, initiating a process that will fundamentally alter the comet's appearance and behavior. The physics of sublimation, the direct transition from solid to gas without passing through a liquid phase, governs the comet's awakening under solar influence. Water ice, which comprises the majority of the comet's volatile materials, begins to sublimate at temperatures around -160 degrees Celsius under the low-pressure conditions of space. As solar heating raises the surface temperature above this threshold, water molecules escape directly from the solid ice matrix, carrying with them embedded dust particles and creating the first wisps of the comet's atmosphere, or coma. This atmospheric envelope forms gradually around the nucleus, starting as an invisible shell of water vapor that extends only a few kilometers from the surface. The escaping gas molecules follow ballistic trajectories away from the nucleus, their motion governed by the weak gravitational field of the small comet and the pressure of continued sublimation from below. As more ice sublimes, the coma grows in size and density, eventually becoming visible to telescopes as a fuzzy halo surrounding the star-like point of the nucleus. The rate of sublimation depends not only on solar heating, but also on the composition and structure of the comet's surface layers. The dark, organic-rich mantle that has protected the pristine interior for millions of years now acts as both insulation and catalyst for the sublimation process. This protective layer, formed by the gradual accumulation of non-volatile materials left behind by previous sublimation episodes, contains pockets and fissures that can suddenly rupture under the pressure of escaping gases, creating localized jets of vapor and dust that fountain away from the nucleus in spectacular displays of activity. The comet's rotation, with a period measured in hours rather than days, creates a complex pattern of heating and cooling across its surface. As different regions of the nucleus rotate into sunlight, they experience cycles of warming and sublimation that create asymmetric patterns of gas and dust emission. This rotational modulation of activity means that the comet's brightness and the structure of its developing coma vary cyclically as seen from Earth, providing astronomers with clues about the nucleus's shape, composition, and rotation period. The scientific mystery surrounding the comet's initial response to solar heating lies in predicting exactly when and how dramatically its activity will begin. Different volatile materials sublimate at different temperatures, carbon monoxide and nitrogen at much lower temperatures than water, while organic compounds may require significantly more heating. The sequence and intensity of these sublimation processes depend on the comet's detailed composition and internal structure, properties that remain largely unknown until direct observation reveals the comet's behavior under solar influence. Only took 1 million years to travel this far just to start melting. The irony emerges from the comet's patient journey across interstellar space, preserving its pristine materials in perfect frozen suspension, only to begin losing them to the vacuum of space as soon as it encounters sufficient solar heating. The very warmth that awakens the comet also begins its destruction, creating the spectacular displays that make comets visible to human observers while simultaneously depleting the ancient reserves of ice and dust that the nucleus has carried since its formation. Another ironic aspect of the comet's solar awakening concerns the relationship between distance and activity. While the comet remains farther from the Sun than Jupiter and experiences only a fraction of the solar heating that Earth receives, this modest warming proves sufficient to trigger dramatic changes in its appearance and behavior. The vast difference between interstellar and interplanetary temperatures means that even the outer regions of the solar system feel tropical compared to the cosmic deep freeze from which the comet has emerged. The third irony lies in the comet's development of a tail while still moving toward the Sun rather than away from it. Unlike the intuitive expectation that tails should stream behind moving objects, comet tails always point away from the Sun regardless of the comet's direction of motion. This creates the counterintuitive situation where the comet appears to be leading with its tail as it approaches the inner solar system, a configuration that violates terrestrial expectations about the relationship between motion and aerodynamic drag. The formation of the comet's first tentative tail occurs through the interaction between the developing coma and the solar wind, a continuous stream of charged particles flowing outward from the Sun at speeds of several hundred kilometers per second. As water molecules in the coma become ionized by solar ultraviolet radiation, they respond to the magnetic field carried by the solar wind, creating a faint plasma tail that extends away from the Sun in the direction of the wind flow. This ionization process operates independently of the comet's orbital motion, ensuring that the tail always points away from the Sun regardless of whether the comet is approaching or receding. Simultaneously, solar radiation pressure begins to act on the dust particles released by sublimation, pushing them away from the nucleus through the momentum transfer of photons. This radiation pressure, negligible for large objects but significant for microscopic dust grains, creates a separate dust tail that follows a slightly different trajectory than the plasma tail. The dust tail, typically appearing yellowish or white due to reflected sunlight, curves gently away from the Sun following the orbital motion of the ejected particles. The spectroscopic analysis of light from the developing coma provides astronomers with detailed information about the comet's composition and the physical processes occurring in its atmosphere. Different molecular species emit characteristic wavelengths of light when excited by solar radiation, creating a fingerprint that reveals the presence of water, carbon dioxide, carbon monoxide, and various organic compounds. These observations allow scientists to compare the composition of interstellar material preserved in the comet with that of objects that formed within our solar system. As the sublimation process continues, the comet's nucleus begins to develop an irregular, sculpted appearance as different regions respond differently to solar heating. Areas rich in volatile materials create valleys and depressions as sublimation removes material, while regions with higher concentrations of rocky or organic matter remain elevated, creating the complex topography observed on other comet nuclei visited by spacecraft. This differential erosion process gradually reveals the internal structure and composition of the nucleus, providing a three-dimensional view of materials that formed in the early solar system. The rate of mass loss through sublimation, while dramatic compared to the comet's previous dormant state, remains relatively modest in absolute terms. A typical comet nucleus several kilometers in diameter might lose several tons of material per second at this distance from the Sun, a rate that could continue for many orbits before significantly depleting the nucleus. This gradual erosion ensures that the comet can maintain its activity over multiple passages through the inner solar system, providing repeated opportunities for observation and study. The comet's growing voice, expressed through the expanding coma and developing tails, marks its transition from invisible wanderer to spectacular celestial display. Yet this transformation represents only the beginning of its solar awakening. As 3I/Atlas continues its approach toward the Sun, the intensity of solar heating will increase dramatically, triggering more vigorous sublimation and creating the magnificent tail displays that have inspired human imagination throughout recorded history. The ancient ice that has slumbered in the cosmic cold now begins its brief but brilliant performance under the spotlight of our star. As Comet 3I/Atlas continues its journey deeper into the solar system, its motion begins to follow the mathematical poetry written in the language of orbital mechanics. The gravitational encounters with distant planets and the growing influence of solar radiation have refined the comet's trajectory, setting it onto a precise elliptical path that demonstrates the elegant geometry underlying all celestial motion. This orbital dance, governed by the same fundamental laws that control the movement of planets and moons, represents one of the most beautiful expressions of mathematical physics in the natural world. The mathematics describing the comet's orbital motion trace their origins to Johannes Kepler's revolutionary insights in the early 17th century. Later refined and generalized by Newton's law of universal gravitation and Einstein's general theory of relativity, Kepler's three laws of planetary motion, derived from painstaking observations of Mars's orbit, apply with equal validity to every object orbiting the Sun, from the smallest asteroid to the most massive planet. The comet's path through space follows these mathematical relationships with the precision of clockwork, its position at any future time calculable through equations that reveal the underlying order governing celestial mechanics. The comet's orbital elements, 6 parameters that completely describe its trajectory through three-dimensional space, encode the entire history of its gravitational interactions with the solar system. The semi-major axis defines the size of the elliptical orbit, determining the comet's orbital period through Kepler's third law. The eccentricity describes the shape of the ellipse, ranging from 0 for a perfect circle to values approaching 1 for highly elongated orbits that barely remain gravitationally bound to the Sun. The inclination angle measures how steeply the orbital plane tilts relative to the ecliptic plane defined by Earth's orbit around the Sun. 3 additional angular parameters, the longitude of ascending node, argument of perihelion, and mean anomaly at epoch, specify the orientation of the orbital ellipse in space and the comet's position along that ellipse at any given time. These 6 numbers, derived from careful observations of the comet's position and velocity, contain enough information to predict its location months or years into the future, demonstrating the deterministic nature of gravitational physics despite the apparent complexity of multi-body interactions. The mathematical precision of orbital prediction represents one of the greatest triumphs of theoretical physics, yet the actual computation of comet trajectories requires sophisticated numerical methods to account for perturbations from multiple gravitational sources. While the two-body problem of a comet orbiting the Sun admits exact analytical solutions, the real solar system contains multiple massive planets whose gravitational influences create a complex, many-body problem that defies simple mathematical treatment. Modern orbital calculations employ numerical integration techniques that break the comet's motion into tiny time steps, computing the cumulative effects of all gravitational forces acting on the nucleus at each moment. The stability of the comet's newly established orbit depends critically on its energy relative to the Sun's gravitational field. Objects with negative total energy remain permanently bound to the solar system, following closed elliptical paths that return them periodically to the inner planets. Positive energy trajectories represent unbound hyperbolic orbits that carry objects through the solar system once before ejecting them back to interstellar space. The boundary between these regimes occurs at zero total energy, corresponding to parabolic trajectories that approach infinite orbital periods. For Comet 3 I/Atlas, the gravitational encounters with outer planets have nudged its trajectory tantalizingly close to this critical boundary between bound and unbound motion. Small perturbations from planetary gravity, solar radiation pressure, or even the asymmetric outgassing of sublimating ice could tip the energy balance in either direction. Determining whether the comet will become a permanent member of our solar system's population or continue its journey toward the stars. This delicate balance illustrates the chaotic sensitivity that characterizes orbital dynamics at the margin between order and escape. The scientific mystery surrounding the comet's long-term orbital evolution lies in predicting how various non-gravitational forces will affect its trajectory over multiple orbital periods. The asymmetric sublimation of ice from the rotating nucleus creates tiny but persistent rocket-like forces that can gradually alter the comet's orbit over time. These non-gravitational perturbations, while small compared to planetary gravity, accumulate over many orbits to produce significant changes in orbital elements, making long-term predictions increasingly uncertain. Solar radiation pressure adds another layer of complexity to orbital calculations, particularly for small particles ejected from the comet's nucleus. While the nucleus itself experiences negligible radiation pressure due to its relatively large mass, the dust and gas released through sublimation can be significantly affected by photon momentum transfer. This differential response to radiation pressure gradually separates the comet's material into distinct populations with slightly different orbital characteristics, creating the complex structure observed in comet tails and the meteoric debris streams that produce annual meteor showers. Only took billions of years for gravity to compose this particular orbital symphony. The irony emerges from the mathematical beauty of celestial mechanics, where the apparently chaotic interactions of multiple massive bodies resolve into elegant geometric patterns that persist for millions of years. The same gravitational forces that create complex perturbations and unpredictable encounters on short timescales generate stable, repeating orbital configurations when viewed from the perspective of deep time. The comet's trajectory, seemingly random in its origin and evolution, now follows mathematical laws of pristine clarity and precision. Another ironic aspect of orbital mechanics concerns the relationship between speed and distance in elliptical orbits. As the comet approaches its closest point to the Sun, it will paradoxically reach its maximum orbital velocity, moving fastest when it experiences the strongest gravitational pull. Conversely, at its most distant point from the Sun, the comet will crawl along its orbital path at minimum velocity, taking years to traverse distances it covers in weeks during its close solar passage. This counterintuitive relationship between position and velocity reflects the conservation of angular momentum that governs all orbital motion. The third irony lies in the precision with which orbital mechanics operates, despite the fundamental randomness underlying quantum physics and the chaotic sensitivity characteristic of many body systems. The macroscopic world of planetary motion follows deterministic classical physics with extraordinary accuracy, allowing astronomers to predict eclipses centuries in advance and navigate spacecraft to distant planets with remarkable precision. Yet this clockwork universe emerges from quantum mechanical processes that exhibit fundamental uncertainty and randomness at their core. The geometry of the comet's elliptical orbit creates a natural rhythm that will govern its future interactions with the solar system. The orbital period, the time required for one complete circuit around the Sun, depends only on the semi-major axis of the ellipse, following Kepler's third law with mathematical precision. For comets with highly elliptical orbits extending far beyond the outer planets, orbital periods can range from decades to millennia, creating long intervals between successive visits to the inner solar system. The concept of orbital resonance introduces additional complexity to the comet's long-term dynamics, as its orbital period may develop simple numerical relationships with the periods of major planets. These resonances can either stabilize or destabilize comet orbits over long time scales, depending on their specific mathematical ratios. Jupiter's dominant gravitational influence creates a complex web of resonant zones that can trap comets in stable orbital families or eject them from the solar system entirely through chaotic scattering processes. Modern computational astronomy employs sophisticated mathematical techniques to model the comet's orbital evolution over millions of years, using Monte Carlo methods to explore how uncertainties in initial conditions propagate through time. These calculations reveal that, while the comet's position can be predicted with high accuracy for several orbital periods, longer-term predictions become increasingly unreliable due to the exponential growth of small errors characteristic of chaotic dynamical systems. The orbital mechanics governing Comet 3, 1/Atlas, operate according to the same fundamental principles that control the motion of artificial satellites, planetary rings, and binary star systems. This universality of gravitational physics demonstrates one of the most profound insights of modern science, that the same mathematical laws operate throughout the universe. From laboratory experiments to galactic dynamics, the comet's dance around the Sun exemplifies this cosmic unity, its trajectory encoding the fundamental constants of nature and the geometric relationships that govern motion in curved space-time. As the comet settles into its mathematically determined orbital path, it carries with it the accumulated history of every gravitational encounter that shaped its journey through the solar system. The elegant ellipse it now traces through space represents the resolution of countless complex interactions into a single, beautifully simple geometric curve that will guide its motion for years or decades to come, until the next close planetary encounter writes a new chapter in its gravitational story. Within the crystalline matrix of Comet 3, I/Atlas's nucleus, water molecules carry memories that predate the formation of our solar system by hundreds of millions of years. These ancient ice crystals, locked in their frozen lattice for eons, preserve the isotopic signatures and molecular structures that formed in the stellar nurseries where massive stars lived, died, and scattered their enriched materials across interstellar space. As the comet continues its approach toward the Sun, each sublimating water molecule releases not merely vapor into the growing coma, but testimony to the cosmic processes that forged the chemical elements of life itself. The deuterium to hydrogen ratio embedded within these water molecules provides a direct measurement of the conditions that prevailed in the molecular cloud from which our solar system condensed 4.6 billion years ago. Deuterium, the heavy isotope of hydrogen containing both a proton and neutron in its nucleus, forms through specific nuclear processes in stellar interiors and supernova explosions. The abundance of this rare isotope relative to ordinary hydrogen reflects the chemical evolution of our galaxy over billions of years, recording the gradual enrichment of interstellar space with elements heavier than the primordial hydrogen and helium that emerged from the Big Bang. Spectroscopic analysis of the water vapor streaming from 3I/Atlas reveals deuterium enrichment levels that differ subtly but significantly from terrestrial water, suggesting that the comet's ice formed under different conditions than the materials that eventually became Earth's oceans. This isotopic discrepancy provides clues about the temperature and density conditions in the outer regions of the solar nebula, where water ice could condense and accumulate into the building blocks of comets and outer planet systems. The comet thus serves as a frozen archive of solar system formation, preserving samples of the original materials that might otherwise have been lost to planetary processing. The molecular structure of the ice itself tells additional stories about the comet's formation environment. Water molecules trapped within the crystalline lattice often contain other simple compounds: carbon monoxide, carbon dioxide, methane, and ammonia, that were incorporated during the initial freezing process in the cold outer reaches of the solar nebula. These clathrate hydrates, cage-like structures where water molecules surround and trap other molecules, represent some of the most pristine materials available for studying the chemical conditions that prevailed during planetary formation. As solar heating begins to destabilize these ancient ice structures, the sublimation process releases not only water vapor, but also the trapped gases that have remained locked within the crystalline matrix for billions of years. The sequential release of different volatile species as temperature increases provides astronomers with a kind of chemical archaeology, revealing the layered history of the comet's formation and the various episodes of heating and cooling it may have experienced during its long journey through space. The organic compounds mixed throughout the comet's nucleus add another dimension to its role as a chemical time capsule. Complex carbon-based molecules, including amino acids, nucleotide bases, and other prebiotic compounds, formed through radiation-driven chemistry in the cold molecular clouds that preceded solar system formation. These materials, preserved in the comet's frozen interior, may represent some of the same organic building blocks that contributed to the emergence of life on Earth through bombardment by comets and asteroids during the late heavy bombardment period. The scientific mystery surrounding the comet's chemical composition deepens when researchers attempt to compare its materials with those found in meteorites, asteroids, and other solar system objects, while broad similarities suggest a common origin in the solar nebula. Subtle differences in isotopic ratios and molecular abundances hint at spatial variations in the composition of the original molecular cloud. These chemical gradients provide clues about the physical processes that mixed and segregated materials during the collapse of the solar nebula into the Sun and planets. The challenge of interpreting the comet's chemical signatures becomes more complex when considering the effects of cosmic ray bombardment and solar wind interaction during its million-year journey through interstellar space. High-energy particles from distant supernovae and galactic cosmic ray sources can alter the isotopic composition of surface materials through nuclear spallation reactions, potentially obscuring the original chemical fingerprints. Distinguishing between primordial compositions and radiation-induced modifications requires careful analysis of how different isotopes respond to cosmic ray exposure. Only took the death of countless stars to create these particular water molecules. The irony emerges from the violent stellar processes required to forge the heavy elements that make water possible, oxygen nuclei synthesized in the cores of massive stars and scattered through supernova explosions, then mixed with hydrogen in the cold depths of molecular clouds to create the most common molecule in the universe after molecular hydrogen. The peaceful sublimation of ice from the comet's surface represents the gentle conclusion of nuclear processes that involve temperatures of millions of degrees and pressures exceeding those in planetary cores. Another ironic observation concerns the preservation of stellar chemistry within ice that formed in some of the coldest environments in the universe. The molecular clouds where cometary ice condensed maintain temperatures only a few degrees above absolute zero. Yet these frigid conditions proved ideal for preserving the chemical signatures of stellar nucleosynthesis that occurred at temperatures exceeding those in the Sun's core. The comet's nucleus thus represents a kind of cosmic freezer that has maintained samples of stellar chemistry in pristine condition for billions of years. The third irony lies in the relationship between the comet's ancient materials and the relatively recent solar system it now visits. While the water molecules and organic compounds in the nucleus predate the formation of the Sun and planets, the comet's current orbital configuration and its interaction with solar radiation represent entirely new chapters in the history of these ancient materials. The stellar chemistry preserved in the ice remains unchanged from its formation in distant molecular clouds. Yet the context in which this chemistry now expresses itself has been completely transformed by the gravitational and radiative environment of our solar system. The process of sublimation creates a natural mass spectrometer as different volatile species escape from the nucleus at different rates depending on their molecular weights and vapor pressures. Water ice, comprising perhaps 80% of the nucleus by mass, dominates the sublimation process at temperatures above 150 Kelvin, while more volatile species like carbon monoxide and nitrogen escape at much lower temperatures. This differential sublimation creates a stratified structure in the developing coma, with different molecular species concentrated at different distances from the nucleus. The isotopic ratios measured in these sublimating gases provide direct constraints on models of galactic chemical evolution and solar system formation. The abundance of heavy water, molecules containing deuterium instead of ordinary hydrogen, reflects the balance between destruction through stellar nucleosynthesis and production through cosmic ray spallation and chemical fractionation in cold molecular clouds. Comparing these ratios with those found in terrestrial water, Martian meteorites, and samples from other solar system objects helps astronomers reconstruct the chemical evolution of our local galactic neighborhood. Modern analytical techniques allow astronomers to detect not only the major molecular species in the comet's coma, but also trace amounts of exotic compounds that provide additional insights into the chemical processes operating in stellar atmospheres and molecular clouds. Isotopologues, molecules with the same chemical formula but different isotopic compositions, serve as sensitive tracers of the temperature and radiation conditions that prevailed during the comet's formation. These measurements require extraordinarily sensitive spectrometers capable of detecting parts per million differences in the wavelengths of light emitted by different isotopic variants of the same molecule. The study of cometary chemistry thus provides a unique window into the processes that operated in the pre-solar molecular cloud, offering direct samples of materials that predated the formation of our planetary system. As each water molecule escapes from the nucleus and disperses into space, it carries with it not only the hydrogen and oxygen atoms forged in ancient stellar cores, but also the isotopic signatures and molecular memories that connect our solar system to the broader galactic community of stars and the cosmic chemical evolution that has enriched the universe with the elements necessary for planets, atmospheres, and life itself. Each passage of Comet 3 I/Atlas near the Sun leaves behind an invisible legacy scattered along its orbital path, a trail of microscopic particles that will persist in space for thousands of years after the comet itself has moved on. These dust grains, liberated from the nucleus through the gentle violence of sublimation, follow trajectories that slightly diverge from the comet's orbit, creating an expanding cloud of debris that eventually spreads throughout the inner solar system. The gravitational perturbations of planets and the subtle pressure of solar radiation gradually disperse these particles into complex patterns that map the comet's orbital history across geological time. The physics governing the motion of these ejected particles involves a delicate interplay between gravity, radiation pressure, and the initial velocity imparted by the sublimation process. Dust grains launched from the comet's surface carry momentum inherited from the nucleus's rotation and the expanding gases that lifted them into space. Once free of the comet's weak gravitational field, these particles begin independent orbits around the Sun, their trajectories determined by their size, composition, and the precise circumstances of their ejection from the parent nucleus. Solar radiation pressure plays a crucial role in shaping the long-term evolution of the dust trail, particularly for the smallest particles that comprise the majority of ejected material. Photons carrying momentum from the Sun transfer tiny amounts of energy to dust grains through absorption and reflection, creating a force that acts continuously throughout the particle's orbital motion. This radiation pressure effect, negligible for objects larger than a few millimeters, becomes dominant for microscopic grains, gradually spiraling them inward toward the Sun or outward toward the outer solar system, depending on their optical properties and orbital characteristics. The size distribution of particles in the dust trail follows a power law relationship that reflects the fragmentation processes operating within the comet's nucleus. Larger particles, ranging from pebbles to boulders, resist the gentle forces that lift smaller material into space, remaining concentrated near the nucleus until more vigorous sublimation events provide sufficient energy for their ejection. Microscopic dust grains, with diameters measured in micrometers, escape more easily and comprise the majority of material lost from the comet during its passage through the inner solar system. The composition of these particles mirrors that of the nucleus itself, containing a mixture of silicate minerals, organic compounds, and residual ice that survives the initial sublimation process. As the particles continue their independent orbits, solar heating gradually removes any remaining volatile materials, leaving behind refractory grains of rock and carbonaceous compounds that can survive for millions of years in the harsh radiation environment of interplanetary space. These processed particles eventually contribute to the zodiacal dust cloud that fills the inner solar system and creates the faint glow visible along the ecliptic plane during twilight hours. The orbital dynamics of the dust trail create complex three-dimensional structures that evolve over time through gravitational perturbations and radiation effects. Particles ejected during different passages of the comet spread out along its orbital path, creating multiple streams of debris that may eventually merge or separate depending on their specific orbital elements. The largest particles tend to cluster near the comet's original orbit, while smaller grains disperse more widely under the influence of radiation pressure and planetary perturbations. When Earth's orbit intersects these particle streams, the result is a meteor shower that can persist for days or weeks as our planet sweeps through the debris field. The meteors visible during these events represent the final moments in the billion-year journey of materials that originated in distant stellar atmospheres, condensed in cold molecular clouds, survived the formation of the solar system, and finally ended their cosmic odyssey in brilliant flashes of light in Earth's upper atmosphere. The scientific mystery surrounding the dust trail's evolution lies in predicting how gravitational resonances with major planets will affect the long-term distribution of particles. Computer models can track the motion of individual dust grains for centuries or millennia, but the chaotic nature of multi-body gravitational interactions makes longer-term predictions increasingly uncertain. Small differences in initial conditions, the exact time and location of particle ejection, tiny variations in size or density can lead to dramatically different evolutionary pathways over geological timescales. Only took 1 billion years for stellar materials to become shooting stars. The irony emerges from the cosmic journey that brings heavy elements forged in stellar cores to their spectacular destruction in Earth's atmosphere. The same silicon, magnesium, and iron atoms that underwent nuclear fusion in the hearts of massive stars survive supernova explosions, condensed in molecular clouds, and aggregated into comet nuclei. Ultimately meet their fate as brief streaks of light lasting mere seconds in our planet's protective atmosphere. Another ironic aspect of the dust trail's formation concerns the relationship between creation and destruction in the comet's activity. The same sublimation process that creates the spectacular visual displays making comets famous also gradually dismantles the nucleus, scattering its ancient materials throughout the solar system. Each magnificent tail that streams behind the comet represents an irreversible loss of primordial material, turning the comet's closest approaches to the Sun into both its most glorious and most destructive moments. The third irony lies in the invisibility of the dust trail itself compared to the spectacular meteor showers it eventually produces. While the particles scattered along the comet's orbit remain completely invisible to human observers, their brief interaction with Earth's atmosphere creates some of the most beautiful and dramatic astronomical phenomena visible to the naked eye. The dust trail thus represents a vast reservoir of potential meteors, waiting for the chance orbital alignment that will transform invisible cosmic debris into brilliant celestial fireworks. The study of meteor shower particles provides astronomers with direct samples of cometary material that can be collected and analyzed in terrestrial laboratories. These cosmic dust particles, recovered from high-altitude aircraft flights or Antarctic ice deposits, preserve organic compounds and mineral structures that formed in the original solar nebula. The chemical analysis of these materials provides ground truth for theoretical models of comet composition and helps constrain the conditions that prevailed during the early stages of solar system formation. The temporal evolution of meteor showers reflects the complex orbital dynamics that govern the motion of dust particles over multiple orbital periods. Young meteor showers, associated with recently active comets, tend to produce intense but brief displays as Earth encounters dense concentrations of freshly ejected material. Older meteor streams become more dispersed and produce weaker but longer-lasting showers as gravitational perturbations spread the particles over wider regions of space. The interaction between dust particles and planetary atmospheres creates natural laboratories for studying high-velocity impact phenomena and the chemistry of materials heated to extreme temperatures. When meteoroids enter Earth's atmosphere at speeds of 20 to 70 kilometers per second, the resulting friction heating vaporizes both the particle and atmospheric molecules, creating the luminous plasma trails that define meteoric phenomena. The spectroscopic analysis of these brief flashes provides information about both the composition of the original cometary material and the physics of hypersonic atmospheric entry. Modern meteor detection networks employ automated cameras and radar systems to track thousands of meteoric events each night, building comprehensive databases of particle orbits and compositions that can be traced back to their parent comets. These observations reveal the complex relationship between cometary activity and meteor shower characteristics, showing how variations in the comet's sublimation patterns and orbital evolution influence the timing, intensity, and duration of the resulting meteor displays. The dust trail of Comet 3 Y/Atlas thus represents far more than a simple byproduct of sublimation. It constitutes a permanent modification to the architecture of the inner solar system, adding new streams of particles to the complex web of debris that fills interplanetary space. These materials will continue their orbital dance around the Sun long after the comet itself has exhausted its volatile reserves or been ejected from the solar system, serving as monuments to the cosmic processes that shaped our planetary neighborhood and continuing reminders of the connection between stellar evolution and the everyday phenomena visible in our night sky. As Comet 3 I/Atlas approaches the inner solar system, it encounters an invisible wind that has blown continuously from the sun for billions of years. The solar wind, a plasma stream of charged particles accelerating away from our star at speeds approaching 400 kilometers per second, carries with it the magnetic field lines that originated deep within the sun's convective interior. When this magnetized plasma encounters the expanding gases of the comet's coma, it initiates a complex electromagnetic interaction that sculpts one of the most ethereal and beautiful phenomena in the solar system, the plasma tail that will soon stream behind the nucleus like a cosmic banner. The solar wind consists primarily of protons and electrons stripped from hydrogen atoms in the sun's corona, along with smaller numbers of helium nuclei and heavier ions that reveal the nuclear processes operating within our star. These particles carry kinetic energies equivalent to temperatures of millions of degrees. Despite the plasma's extremely low density, typically only a few particles per cubic centimeter at Earth's orbital distance, the wind's magnetic field, frozen into the plasma and carried outward from the sun, creates a complex three-dimensional structure that spirals through the solar system due to the sun's rotation. As water molecules and other neutral gases escape from the comet's nucleus through sublimation, they enter an environment dominated by solar ultraviolet radiation intense enough to ionize a significant fraction of the expanding material. This photoionization process strips electrons from water molecules, carbon dioxide, and other species, creating a population of positively charged ions that can interact electromagnetically with the solar wind's magnetic field. The newly formed ions, initially moving with the neutral gas at relatively low speeds, find themselves suddenly subject to magnetic forces that can accelerate them to much higher velocities. The interaction between cometary ions and the solar wind magnetic field operates through a process called mass loading, where the plasma flowing from the sun picks up additional charged particles from the comet's ionosphere. This process transfers momentum from the solar wind to the cometary material, accelerating ions away from the nucleus along magnetic field lines that always point radially outward from the sun. The result is a narrow, straight tail of ionized gas that extends millions of kilometers into space, regardless of the comet's orbital motion or the direction of its velocity vector. The distinctive blue color of the plasma tail arises from fluorescent emission by ionized carbon monoxide molecules excited by solar ultraviolet radiation. When these ions absorb ultraviolet photons, they temporarily store the energy in excited electronic states before re-emitting it as visible light at specific wavelengths that appear blue to human perception. Other ionic species contribute additional colors to the tail's spectrum: ionized water producing red and green emissions, ionized carbon dioxide adding blue-white light, and various organic compounds creating fainter emissions across the visible spectrum. The plasma tail structure reveals the complex magnetic topology of the solar wind as it flows past the comet. Magnetic field lines draped around the nucleus create a magnetotail configuration similar to that found behind planets with magnetic fields, complete with current sheets and magnetic reconnection events that can produce sudden brightenings and structural changes in the tail. These dynamic phenomena occur on timescales ranging from minutes to hours, creating a constantly evolving display that reflects the variable conditions in the solar wind and the fluctuating rate of ion production in the coma. The scientific mystery surrounding plasma tail formation lies in understanding the detailed physics of how solar wind magnetic fields couple to the cometary ionosphere. The interaction involves complex magnetohydrodynamic processes that operate across multiple spatial and temporal scales, from the microscopic motion of individual charged particles to the macroscopic flow patterns that shape the tail's overall structure. Theoretical models must account for the effects of magnetic reconnection, plasma instabilities, and turbulent mixing that can dramatically alter the expected behavior of the ionized gas. Spacecraft missions to comets have revealed that the plasma environment around these objects is far more complex than early theoretical models predicted. The European Space Agency's Rosetta mission, which accompanied Comet 67P/Churyumov-Gerasimenko for more than 2 years, discovered intricate magnetic field structures, plasma density variations, and ion acceleration mechanisms that challenge conventional understanding of comet solar-wind interactions. These observations show that each comet creates its own unique electromagnetic environment that depends on its composition, activity level, and orientation relative to the solar wind flow. Only took 4.5 billion years for the Sun to perfect this cosmic hairstyling technique. The irony emerges from the solar wind's role as both creator and destroyer of cometary tails. The same plasma flow that ionizes cometary gases and creates the beautiful tail displays also gradually strips away the comet's atmosphere, contributing to the long-term erosion that will eventually exhaust the nucleus's volatile reserves. The tail thus represents both the comet's moment of greatest glory and a symptom of its inevitable demise. Another ironic aspect of plasma tail formation concerns the relationship between visibility and substance. The plasma tail, often the most prominent and spectacular feature visible in comet photographs, contains less mass than a breath of air on Earth. The tail's impressive appearance results from the efficiency of fluorescent emission rather than the quantity of material involved, demonstrating how electromagnetic processes can create magnificent displays from almost infinitesimally small amounts of matter distributed across vast volumes of space. The third irony lies in the plasma tail's independence from the comet's orbital motion, creating the counterintuitive situation where the tail can appear to lead the comet as it approaches the Sun. This electromagnetic phenomenon operates according to entirely different principles than the mechanical processes that govern the formation of dust tails. Yet both types of tails coexist in the same cometary environment, creating complex multi-component structures that reflect the diverse physical processes operating in the solar wind interaction region. The magnetic field carried by the solar wind varies significantly with solar activity, creating corresponding variations in the intensity and structure of cometary plasma tails. During periods of high solar activity, when coronal mass ejections and solar flares increase the density and magnetic field strength of the solar wind, plasma tails can become more prominent and exhibit more dynamic behavior. Conversely, during solar minimum conditions, when the solar wind flows more smoothly and carries weaker magnetic fields, plasma tails may appear fainter and more stable. The study of cometary plasma tails provides astronomers with remote probes of solar wind conditions throughout the solar system, extending direct measurements of the interplanetary medium far beyond the limited number of spacecraft equipped with plasma instruments. By analyzing the morphology and brightness variations of plasma tails, researchers can infer the magnetic field strength, plasma density, and flow velocity of the solar wind at the comet's location, providing valuable data for models of solar wind propagation and evolution. The interaction between the solar wind and cometary plasma also creates natural particle accelerators that can energize ions to much higher speeds than would be possible through thermal processes alone. Magnetic reconnection events and shockwave formations in the plasma tail environment can accelerate particles to energies of several thousand electron volts, creating populations of energetic ions that contribute to the solar wind's own particle population as they stream away from the comet along magnetic field lines. The plasma tail of Comet 3, Ice/Atlas, will serve as a sensitive indicator of the solar wind conditions it encounters during its passage through the inner solar system, providing astronomers with real-time information about the state of the interplanetary medium and the magnetic field environment surrounding our star. As the comet continues its approach toward perihelion, the increasing intensity of solar radiation and solar wind will amplify these electromagnetic interactions, creating ever more spectacular displays that illuminate the invisible magnetic architecture permeating the space between the planets. From observatories scattered across Earth's surface and instruments orbiting in the darkness of space, human eyes, augmented by technology, turn toward the approaching wanderer that carries within its frozen heart the chemical memory of stellar birth and death. Astronomers track Comet 3 Y/Atlas with patient precision, their telescopes following its gradual brightening as it ventures deeper into the solar system's inner sanctum. Each photon that traveled millions of kilometers from the comet's nucleus to reach these sensitive detectors carries information about materials that formed before our sun ignited its nuclear fires, providing a direct link between human curiosity and the cosmic processes that shaped our galactic neighborhood. The art of cometary observation requires extraordinary patience and technical sophistication, as astronomers attempt to extract meaningful data from objects that remain incredibly faint despite their spectacular appearance in long-exposure photographs. Ground-based telescopes must contend with atmospheric turbulence that blurs stellar images and scattered light from urban illumination that drowns out faint celestial phenomena. The most sensitive observations require dark skies far from human habitation, where ancient light from distant objects can be detected against the cosmic background with minimal interference from terrestrial sources. Modern charge-coupled device cameras and complementary metal oxide semiconductor sensors have revolutionized cometary astronomy by providing quantum efficiencies approaching 90%, meaning that nearly every photon striking the detector produces a measurable electronic signal. These digital detectors can accumulate light over periods of hours or even days, building up detailed images of extremely faint objects that would remain invisible to visual observation. The resulting data provides astronomers with precise measurements of the comet's position, brightness, and spectral characteristics that reveal its composition and physical state. Spectroscopic analysis of light from the comet's coma and tails provides the most detailed information about its chemical composition and the physical processes occurring in its atmosphere. High-resolution spectrographs disperse the comet's light into its component wavelengths, revealing the characteristic emission and absorption lines produced by specific molecular species excited by solar radiation. Each molecule creates a unique spectral fingerprint that allows astronomers to identify and measure the abundance of water, carbon dioxide, carbon monoxide, cyanogen, and dozens of other compounds present in the expanding gases. The challenge of cometary spectroscopy lies in separating the faint emissions from the comet's atmosphere from the much brighter reflected sunlight that dominates the nucleus's spectrum. This requires sophisticated data reduction techniques that can model and subtract the solar contribution while preserving the genuine cometary emissions that carry information about the nucleus's composition. Modern spectrographs achieve this separation through careful calibration and mathematical modeling that can detect spectral features representing less than 1% of the total light received from the comet. Space-based observatories provide unique advantages for cometary observations by eliminating atmospheric interference and enabling access to ultraviolet and infrared wavelengths that are absorbed by Earth's atmosphere. The Hubble Space Telescope, with its pristine optical system and stable pointing capabilities, can resolve structural details in comet nuclei and comas that remain invisible to ground-based instruments. Infrared space telescopes like the James Webb Space Telescope can detect thermal emission from dust grains and measure the temperature distribution across the comet's surface as it responds to solar heating. Radio telescopes contribute another dimension to cometary studies by detecting emission lines from molecules like hydroxyl radicals and hydrogen atoms that are produced by the photodissociation of water in the coma. These radio observations provide complementary information about the comet's water production rate and the distribution of neutral gases in the extended atmosphere surrounding the nucleus. The sensitivity of modern radio interferometers allows astronomers to map the three-dimensional structure of the coma and track how sublimation patterns change as different regions of the nucleus rotate into and out of sunlight. The scientific mystery surrounding Comet 3Y/Atlas centers on reconciling remote observations with theoretical models of cometary structure and composition. While spectroscopic measurements can identify the molecular species present in the coma, inferring the composition and physical state of the nucleus requires complex modeling of sublimation processes, gas dynamics, and radiative transfer through the dusty atmosphere. Different assumptions about the nucleus's porosity, thermal conductivity, and surface composition can lead to dramatically different interpretations of the same observational data. The temporal evolution of the comet's brightness and spectral characteristics provides clues about the physical processes occurring within the nucleus as solar heating penetrates beneath the surface. Early observations show primarily carbon monoxide and other highly volatile species that sublimate at very low temperatures, while closer approaches to the Sun reveal increasing amounts of water vapor and more complex organic compounds that require higher temperatures for sublimation. This sequential activation of different volatile reservoirs creates a natural stratigraphy that reflects the thermal structure and composition gradients within the nucleus. Only took several hundred years of telescope development to finally peer into the chemical archives of stellar evolution. The irony emerges from the technological sophistication required to analyze materials that formed through the simplest possible processes: gravitational collapse and radiative cooling in the depths of molecular clouds. The most advanced instruments human ingenuity can devise are needed to decode the messages carried by water molecules and dust grains that assembled themselves through nothing more complex than gentle gravitational attraction and chemical condensation in the cold vacuum of space. Another ironic aspect of cometary observation concerns the relationship between distance and revelation. As the comet approaches the Sun and becomes more active, creating the spectacular displays that make it visible to increasingly modest telescopes. The very processes that enable these observations are simultaneously destroying the pristine materials that make the comet scientifically valuable. The comet becomes most observable precisely when it is least representative of its original state, requiring astronomers to observe carefully and interpret wisely to extract information about primordial conditions from measurements of an actively evolving system. The third irony lies in the precision required to measure the properties of an object whose very nature involves constant change and chaotic variability. Cometary nuclei rotate irregularly, sublimate unpredictably, and fragment unexpectedly. Yet astronomers must extract quantitative measurements of composition, mass, and structure from observations of this inherently dynamic and unstable system. The challenge resembles attempting to characterize a melting ice sculpture while it transforms before the observer's eyes. International collaboration plays a crucial role in cometary observations, as the best viewing conditions for any particular comet vary with geographic location and seasonal timing. Observatories in different hemispheres can provide continuous coverage as Earth's rotation carries individual sites in and out of darkness, while coordinated observing campaigns ensure that critical events like outbursts or fragmentation episodes are captured by multiple independent instruments. These collaborative efforts create comprehensive datasets that no single observatory could obtain independently. Amateur astronomers contribute valuable observations to cometary science, particularly in the areas of discovery and long-term monitoring that require consistent coverage over extended periods. Many comets are initially discovered by dedicated amateur observers using modest telescopes and CCD cameras, their patient scanning of the night sky complementing the targeted observations of professional facilities. The visual observations and photographs contributed by skilled amateurs provide important context for the more specialized measurements obtained with major observatory instruments. Modern data reduction and analysis techniques employ sophisticated algorithms to extract maximum information from cometary observations while accounting for various sources of noise and systematic error. Machine learning approaches can identify subtle spectral features or detect faint structural details that might escape human notice, while statistical analysis techniques can quantify uncertainties and establish confidence levels for derived physical parameters. These computational methods allow astronomers to push the limits of their instruments and extract scientifically meaningful results from observations at the very threshold of detectability. The observations of Comet 3 I/Atlas will contribute to a growing database of cometary properties that helps astronomers understand the diversity of objects in the solar system's reservoir of primitive materials. Each well-observed comet provides a unique window into the conditions that prevailed in different regions of the solar nebula, while statistical studies of large comet samples reveal the broader patterns and correlations that constrain theoretical models of planetary system formation and evolution. As Comet 3 I/Atlas ventures ever closer to the Sun, it enters a realm where tidal forces begin to exert their subtle but inexorable influence on the structure of the nucleus. These gravitational stresses, negligible at the vast distances of the outer solar system, grow stronger with each passing day as the inverse cube law governs their intensity. The same mathematical relationship that creates ocean tides on Earth now operates on a cosmic scale, stretching and compressing the comet's loosely consolidated materials with forces that will ultimately reveal the internal architecture hidden within its ancient ice and dust. Tidal forces arise from the differential gravitational pull that the Sun exerts across the finite size of the comet's nucleus, while the comet as a whole experiences the Sun's gravity as a uniform acceleration toward our star. Different portions of the nucleus lie at slightly different distances from the Sun and therefore experience slightly different gravitational forces. The side of the nucleus closest to the Sun feels a stronger pull than the center of mass. While the far side experiences a weaker attraction, this differential stretches the nucleus along the Sun-comet line while simultaneously compressing it in the perpendicular directions. The mathematical description of tidal forces involves derivatives of the gravitational field, second-order effects that become significant only when the size of the object becomes comparable to the scale over which gravity changes appreciably. For a comet nucleus several kilometers in diameter, approaching within a few million kilometers of the Sun, these forces can generate stresses of several pascals across the nucleus. Modest by terrestrial standards, but potentially significant for materials with the structural integrity of dirty snow or loosely cemented rubble. The internal structure of the comet nucleus determines how it will respond to these mounting tidal stresses. If the nucleus consists of a solid, monolithic block of ice and rock, it can withstand substantial tidal forces without disruption, behaving like a single coherent body throughout its orbital motion. However, most comet nuclei appear to be gravitational aggregates, loosely bound collections of smaller fragments held together by their own weak gravity and the cohesive forces of ice and organic cements. These rubble pile structures prove much more vulnerable to tidal disruption. As tidal stresses increase during the comet's approach to perihelion, they begin to compete with the nucleus's own self-gravity in determining the structural stability of the object. The Roche limit defines the critical distance at which tidal forces exactly balance gravitational self-attraction for a fluid body. But real comet nuclei possess finite structural strength that allows them to survive somewhat closer approaches before succumbing to disruption. The exact distance at which a particular nucleus will fragment depends on its size, density, internal structure, and material properties. The process of tidal disruption rarely occurs as a sudden catastrophic explosion, but more commonly manifests as gradual weakening and eventual separation of distinct components within the nucleus. Pre-existing fractures and planes of weakness, perhaps created during the original accretion process or subsequent collisional evolution, provide preferential sites where tidal stresses can initiate fragmentation. The rotation of the nucleus adds centrifugal forces that can accelerate the disruption process, by reducing the effective gravitational binding of surface materials. Observational evidence for tidal effects appears in the form of jets, outbursts, and structural changes that occur preferentially during close solar approaches. As internal stresses mount, weak regions within the nucleus may suddenly rupture, exposing fresh subsurface materials to solar heating and creating dramatic increases in sublimation activity. These outburst events can temporarily increase the comet's brightness by several magnitudes while ejecting substantial amounts of gas and dust into the surrounding coma. The scientific mystery surrounding tidal disruption lies in predicting exactly when and how a particular nucleus will respond to mounting gravitational stresses. The internal structure of comet nuclei remains largely unknown, hidden beneath opaque surface layers that prevent direct observation of the interior architecture. Theoretical models must rely on indirect evidence from surface morphology, rotation periods, and sublimation patterns to infer the likely distribution of strengths and weaknesses within the nucleus. Recent spacecraft missions to comets have revealed complex internal structures that challenge simple models of homogeneous ice-rock mixtures. The nucleus of Comet 67P/Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission, exhibits a bilobed structure that suggests either formation through the merger of two separate objects or subsequent erosional processes that carved away a connecting neck region. These observations highlight the diversity of possible internal architectures and the difficulty of predicting how any particular nucleus will respond to tidal stresses. Only took billions of years for gravity to write the structural specifications for its own architectural limits. The irony emerges from the same gravitational force that initially assembled the comet nucleus from countless smaller particles, now threatening to tear it apart as the nucleus ventures too close to a much more massive object. The gentle gravity that gradually accumulated cosmic dust and ice into a coherent body over millions of years can be overwhelmed in a matter of hours by the differential gravitational field of a star encountered in the nucleuses wandering through space. Another ironic aspect of tidal disruption concerns the relationship between the comet's most spectacular phase and its most vulnerable moment. As the nucleus approaches close enough to the Sun to create magnificent tail displays visible across interplanetary distances, it simultaneously enters the zone where tidal forces pose the greatest threat to its structural integrity. The cosmic circumstances that make comets most beautiful and observable also represent the conditions most likely to destroy them through gravitational dismemberment. The third irony lies in the way tidal forces reveal internal structures that would otherwise remain forever hidden from observation. The same stresses that threaten to destroy the nucleus also provide the only means of probing its interior composition and architecture. Turning the comet's approach to the Sun into a natural experiment in materials science conducted on a cosmic scale, the nucleus becomes most scientifically revealing precisely when it faces the greatest risk of annihilation. The mathematical analysis of tidal disruption involves complex calculations that must account for the nucleus's irregular shape, heterogeneous composition, and rotation-induced stresses. The classical Roche limit, derived for fluid bodies in circular orbits, provides only a rough approximation for real comet nuclei that possess finite strength and follow highly elliptical trajectories. More sophisticated models employ finite element analysis and computational fluid dynamics to simulate how stresses propagate through materials with realistic mechanical properties and structural complexity. The timing of tidal disruption events can provide valuable constraints on the internal structure and composition of comet nuclei. Nuclei that fragment at relatively large distances from the Sun must possess particularly weak internal bonds or pre-existing fracture systems, while those that survive very close, solar approaches demonstrate greater structural integrity. The pattern of fragmentation, whether the nucleus splits into two large pieces, crumbles into numerous small fragments, or experiences progressive erosion, reveals information about the distribution of strong and weak regions within the original structure. Historical observations of comet disruptions provide a database of natural experiments that help astronomers understand the range of possible internal structures and material properties. Comet Shoemaker-Levy 9, torn apart by Jupiter's tidal forces in 1992 and subsequently observed to impact the planet, demonstrated that some nuclei consist of loosely bound rubble piles that can be disrupted by relatively modest tidal stresses. Other comets have survived much closer approaches to the Sun without obvious fragmentation, suggesting more coherent internal structures. The fragments produced by tidal disruption follow slightly different orbits that gradually separate over time, creating multiple comet nuclei from a single parent body. These fragment families can persist for many orbital periods, producing related meteor streams when their debris eventually intersects Earth's orbit. The Great Comet of 1882 spawned a family of sun-grazing comets that continue to return to the inner solar system on similar orbits, demonstrating the long-term consequences of tidal disruption events. Sublimation-driven activity can either accelerate or inhibit tidal disruption depending on the specific circumstances of the nucleus's structure and composition. Gas pressure from sublimating ice can act to hold fractures closed, providing additional structural support that helps the nucleus resist tidal stresses. Conversely, if sublimation occurs preferentially along fracture planes or at interfaces between different materials, the resulting gas pressure can act as a wedge that accelerates the separation of weakly bound components. The dust and gas released during disruption events carry isotopic and chemical signatures that provide direct samples of the nucleus's interior composition. These materials, previously shielded from space weathering and solar radiation by overlying layers, preserve more pristine records of the original chemical and isotopic compositions established during the comet's formation. Spectroscopic analysis of disruption ejecta thus offers unique insights into the unmodified materials from which comet nuclei originally assembled. Modern computational models of tidal disruption employ sophisticated algorithms that can simulate the complex interplay between gravitational stresses, material strength, gas pressure, and thermal effects operating within realistic comet nucleus structures. These simulations require detailed knowledge of ice mechanics, fracture propagation, and the rheological properties of mixed ice-dust materials under the extreme conditions of temperature and pressure found in comet nuclei. The results help astronomers interpret observations and predict the likelihood of disruption for newly discovered comets. The observation of tidal disruption events requires careful monitoring with high-resolution telescopes capable of detecting the subtle changes in brightness and morphology that accompany nucleus fragmentation. Space-based observatories provide the stable viewing conditions necessary to track the evolution of disruption events over periods of days to weeks, while ground-based telescopes contribute the large apertures needed to detect faint fragments and measure their orbital motions. As Comet 3 I/Atlas continues its journey toward the Sun, tidal forces will continue to probe the hidden architecture of its nucleus, testing the strength of bonds forged in the cold darkness of the early solar system against the relentless mathematical precision of gravitational stress. Whether the nucleus survives intact or succumbs to tidal disruption will depend on the specific details of its internal structure and composition, properties that can only be revealed through this ultimate test of cosmic engineering conducted in the laboratory of space itself. The moment of perihelion approaches with astronomical inevitability, marking the culmination of Comet 3 I/Atlas's million-year journey from the cold depths of interstellar space to its closest encounter with our star. At this critical point in its orbit, the ancient wanderer will pass within mere millions of kilometers of the Sun's surface, experiencing temperatures and radiation intensities that will trigger the most dramatic displays of its entire existence. The mathematical precision of orbital mechanics ensures that this cosmic appointment occurs exactly when and where Kepler's laws dictate, transforming the comet from a faint telescopic object into a brilliant beacon visible even in daylight skies. The approach to perihelion represents the moment of maximum solar heating, when the inverse square law of radiation intensity delivers energy to the nucleus at rates thousands of times greater than those experienced in the outer solar system. Surface temperatures that remained near absolute zero for eons now climb rapidly toward the sublimation points of increasingly refractory materials. Water ice, which dominated the comet's activity throughout most of its approach, now yields to more exotic species as carbon dioxide, carbon monoxide, and complex organic compounds begin to sublime in earnest from the superheated surface layers. The geometry of perihelion passage determines the specific conditions the comet will experience during its brief but intense solar encounter. The orbital elements established by gravitational interactions with outer planets dictate not only the minimum distance from the Sun, but also the speed at which the comet will sweep through this critical region. At perihelion, the comet reaches its maximum orbital velocity, potentially exceeding 50 kilometers per second as it whips around the Sun in a hyperbolic arc that demonstrates the elegant conversion between potential and kinetic energy described by conservation laws. The sublimation rate increases exponentially with temperature, following the Clausius-Clapeyron equation that relates vapor pressure to thermal energy. As the nucleus approaches within a few million kilometers of the Sun, the rate of mass loss can increase by orders of magnitude compared to the gentle outgassing observed at greater distances. This dramatic escalation in activity creates gas production rates measured in tons per second, filling the inner solar system with expanding clouds of vapor and dust that scatter sunlight across millions of cubic kilometers of space. The solar wind pressure reaches its maximum intensity near the Sun, creating the strongest electromagnetic forces the comet will encounter during its orbital journey. The plasma environment in this region exhibits extreme variability, with shockwaves, magnetic reconnection events, and turbulent mixing creating complex structures in the developing plasma tail. The interaction between the comet's ionosphere and the intense solar wind generates some of the most spectacular tail phenomena observable from Earth, including disconnection events where magnetic field reversals can sever and reform entire sections of the plasma tail. Radiation pressure from sunlight becomes increasingly significant for the finest dust particles ejected from the nucleus, accelerating microscopic grains to speeds that can exceed the comet's orbital velocity. This process creates the distinctive curved dust tail that streams away from the Sun, its curvature determined by the balance between solar gravity and radiation pressure for particles of different sizes. The largest dust grains follow trajectories that closely approximate the comet's orbit, while the smallest particles are blown straight outward from the Sun in nearly radial paths. The scientific challenge of perihelion observations lies in studying an object that may be too close to the Sun for safe telescope operation, while simultaneously experiencing its most dramatic and scientifically valuable phase of activity. Solar observatories equipped with coronagraphs can sometimes track sun-grazing comets through their closest approaches, but most observational campaigns must rely on measurements obtained before and after perihelion passage to infer the conditions experienced during the critical encounter. The thermal stress experienced by the nucleus during perihelion passage can trigger explosive outbursts as subsurface ice suddenly encounters temperatures far above the sublimation point. These thermal shock events can fracture the protective surface crust, exposing fresh volatile-rich materials to direct solar heating and creating sudden spikes in gas and dust production. The resulting outbursts can temporarily increase the comet's brightness by several magnitudes while ejecting substantial amounts of material into space. The nucleus undergoes its most rapid evolution during the brief period around perihelion, potentially losing several meters of surface material through sublimation and thermal erosion. This mass loss reshapes the nucleus's surface topography, creating new valleys and exposing different compositional layers that reflect the stratified structure established during the original accretion process. The uneven heating of the irregularly shaped nucleus creates complex patterns of thermal stress that can propagate into the interior and influence future activity cycles. Only took 1,000,000 years to travel all this way for a few hours of real drama. The irony emerges from the vast temporal disparity between the comet's long journey through interstellar space and the brief perihelion passage that represents the climax of its entire orbital adventure. The majority of the comet's existence involves patient drifting through cold darkness. Yet, its entire scientific and aesthetic legacy depends on the spectacular displays produced during a few days or weeks of intense solar heating. Another ironic aspect of perihelion passage concerns the relationship between the comet's moment of greatest glory and its most destructive experience. The intense solar heating that creates magnificent tail displays visible across the inner solar system simultaneously represents the most damaging environment the nucleus will encounter. Stripping away ancient materials at rates that could completely exhaust a typical comet nucleus over just a few hundred orbital periods. The comet achieves maximum visibility precisely when it suffers maximum degradation. The third irony lies in the way perihelion passage simultaneously reveals and destroys the pristine materials that make comets scientifically valuable. The intense sublimation triggered by close solar heating provides the only means of accessing the interior composition of the nucleus, bringing subsurface materials to the surface where they can be observed spectroscopically. Yet this same process irreversibly alters the chemical and physical state of these materials, transforming them from their original pristine condition into processed gases and dust dispersed throughout the solar system. The extreme conditions near perihelion create natural laboratories for studying phase transitions, shockwave physics, and plasma interactions under circumstances impossible to replicate in terrestrial facilities. The nucleus becomes a unique experimental apparatus where researchers can observe the behavior of materials subjected to rapid heating rates, extreme temperature gradients, and intense radiation fields while operating in the vacuum conditions of space. Historical records of bright comets visible to the naked eye provide evidence that perihelion passages can create spectacular displays visible even from light-polluted urban areas. The Great Comet of 1997, Comet Hale-Bopp, remained visible to unaided observers for over a year due to its large nucleus and favorable viewing geometry. Such events demonstrate the potential for Comet 3, Y/Atlas, to create memorable astronomical displays if its perihelion distance and nucleus composition prove suitable for dramatic activity. The aftermath of perihelion passage reveals how the nucleus has been modified by its intense solar encounter through changes in rotation period, surface morphology, and subsequent activity patterns. Some comets exhibit delayed outbursts weeks or months after perihelion as thermal waves penetrate into the interior and encounter buried volatile deposits. Others show permanently altered activity levels, reflecting changes in the surface structure that affect the efficiency of heat conduction and gas escape. The orbit of Comet 3 I/Atlas beyond perihelion will be determined by the cumulative effects of gravitational perturbations, solar radiation pressure, and the rocket-like forces produced by asymmetric outgassing during its close solar approach. These non-gravitational forces can significantly modify the comet's trajectory, potentially changing it from a hyperbolic escape orbit to an elliptical bound orbit, or vice versa. The precise outcome depends on complex interactions between the nucleus's rotation, surface composition, and thermal properties that can only be determined through careful observation of the comet's post-perihelion behavior. As Comet 3 I/Atlas begins its recession from the Sun, having survived the intense crucible of perihelion passage, a profound transformation gradually overtakes the nucleus and its extended atmosphere. The brilliant displays that marked the comet's closest solar approach begin to fade with the mathematical precision of the inverse square law, as decreasing solar radiation allows the ancient ice to return to its primordial state of frozen dormancy. This transition from active sublimation to quiescent preservation occurs with the same inexorable inevitability that governs all orbital motion, demonstrating the cyclical nature of cometary evolution and the patient rhythms that characterize celestial mechanics. The physics of this cooling process operates through the same thermodynamic principles that govern the initial warming, but now in reverse as the comet retreats to greater distances, where solar heating becomes increasingly ineffective. Surface temperatures that peaked at several hundred degrees above absolute zero during perihelion passage begin their gradual decline toward the cosmic background temperature of 2.7 Kelvin. This cooling occurs more slowly than the initial heating due to thermal inertia within the nucleus, as stored heat slowly conducts outward through the low thermal conductivity mixture of ice, dust, and void space that comprises the nucleus interior. The sublimation rate decreases exponentially as surface temperatures drop below the vapor pressure curves of various volatile species. Water ice, which dominated the gas production during the comet's active phase, becomes the first major constituent to return to dormancy as temperatures fall below the critical threshold for sustained sublimation. More volatile species like carbon monoxide and nitrogen continue outgassing at progressively lower rates until they too succumb to the declining thermal environment and return to solid form within the nucleus. The coma that surrounded the nucleus, with a diffuse atmosphere millions of kilometers in diameter, begins to dissipate as the production rate of new gas molecules falls below the rate at which existing molecules escape to interplanetary space. This dissipation occurs gradually over periods of months or years, as the vast scale of the coma means that gas molecules ejected during the most active phases require substantial time to travel beyond the region of significant solar heating. The fading coma thus preserves a memory of past activity long after the nucleus itself has returned to dormancy. The magnificent tails that streamed behind the comet for millions of kilometers during its active phase gradually fade and disperse as the supply of new material from the nucleus diminishes. The plasma tail, dependent on the continuous ionization of fresh gas molecules, disappears first as the reduced sublimation rate no longer provides sufficient material to maintain the electromagnetic interaction with the solar wind. The dust tail persists longer, as particles ejected during peak activity continue their independent orbits around the Sun. But these materials gradually spread out along the comet's orbital path until they become too diffuse to observe. The surface of the nucleus undergoes structural changes as thermal stresses induced by rapid heating and cooling create fractures and modify the topography established during previous perihelion passages. The differential thermal expansion and contraction of ice and rocky materials can open new fissures while sealing others, potentially altering the efficiency with which future solar heating will penetrate into the interior. These thermomechanical effects contribute to the gradual evolution of nucleus structure over multiple orbital periods. A new protective mantle begins to form on the nucleus surface as non-volatile materials concentrate in a lag deposit left behind by the sublimation of surrounding ice. This organic-rich layer, darkened by solar radiation and cosmic ray bombardment, will eventually insulate the underlying ice from future solar heating while preserving the chemical signatures of the sublimation process. The formation of this protective crust represents a kind of geological memory that records the history of the nucleus's thermal evolution. The scientific mystery surrounding the post-perihelion evolution of Comet 3/Atlas lies in predicting how the structural and compositional changes experienced during solar heating will affect its future behavior if it returns to the inner solar system. The formation of new fracture systems, the depletion of near-surface volatile deposits, and the development of insulating surface layers all influence how efficiently the nucleus will respond to solar heating during subsequent perihelion passages. The rotation period of the nucleus may change slightly due to the rocket-like forces produced by asymmetric outgassing during the active phase. These non-gravitational torques, while small compared to the gravitational forces that dominate orbital motion, can accumulate over time to produce measurable changes in the nucleus's spin state. The direction and magnitude of these changes depend on the detailed geometry of gas jets and the thermal properties of different regions on the nucleus surface. Only took a few million years to accumulate all this ice just to blow most of it away in a few months. The irony emerges from the vast temporal asymmetry between the slow accretion processes that originally assembled the comet nucleus and the rapid sublimation that strips away these ancient materials during brief episodes of solar heating. The patient work of gravitational aggregation and chemical condensation can be undone in a geological instant when the nucleus ventures too close to a star's radiation field. Another ironic aspect of the comet's return to dormancy concerns the preservation of materials through destruction. The same sublimation process that removes substantial amounts of surface material also creates the protective mantle that will preserve the remaining interior from future thermal damage. The comet sacrifices part of itself to protect what remains, demonstrating a kind of evolutionary adaptation that increases survival probability through partial self-destruction. The third irony lies in the comet's return to invisibility precisely when it has become most scientifically interesting due to the structural and compositional changes induced by solar heating. As the brilliant displays fade and the nucleus becomes too faint for detailed observation, it carries within its modified structure a record of the physical and chemical processes that operated during its active phase. The most valuable scientific information becomes locked away just when the comet disappears from telescopic view. The chemical composition of the nucleus interior may have changed significantly due to thermal processing during perihelion passage. High temperatures can drive chemical reactions between organic compounds and mineral phases that alter the original compositions established during formation in the solar nebula. These thermally induced changes create new molecular species that will be detected only during future active phases, providing evidence of the thermal history experienced by materials in the nucleus interior. The distribution of volatile and refractory materials within the nucleus evolves as sublimation preferentially removes ice from accessible regions while concentrating rocky and organic components in a residual matrix. This process gradually increases the density and mechanical strength of the nucleus while reducing its potential for future activity. Long-term evolution models suggest that repeated perihelion passages will eventually transform active comet nuclei into inert asteroid-like objects depleted of volatile materials. Modern theoretical models of post-perihelion cooling employ sophisticated heat transfer calculations that account for the complex geometry and material properties of realistic comet nuclei. These models predict how thermal waves propagate through the porous interior and influence the timing of volatile freeze-out at different depths within the nucleus. The results help astronomers understand why some comets exhibit delayed activity long after perihelion passage, while others become dormant immediately upon recession from the Sun. The long-term fate of the ejected coma and tail materials depends on their interaction with solar radiation pressure, planetary gravity, and the interplanetary magnetic field. Some particles will eventually spiral into the Sun under radiation pressure, while others may be captured by planetary atmospheres or scattered to the outer solar system. The finest dust grains become part of the zodiacal cloud that creates a faint glow along the ecliptic plane, contributing to the diffuse matter that fills interplanetary space. As Comet 3 I/Atlas continues its recession toward the outer solar system, It enters a phase of patient dormancy that may persist for thousands or millions of years before the next close encounter with stellar radiation. The nucleus carries within its modified structure the accumulated history of all its previous solar encounters, a geological record written in ice and dust that preserves the memory of ancient stellar environments and the dynamic evolution of planetary systems throughout cosmic time. Beyond the orbit of Jupiter, where solar heating becomes insufficient to sustain the dramatic sublimation displays that characterize active comets, 3I/Atlas enters a realm of orbital uncertainty where the mathematical precision of celestial mechanics encounters the chaotic complexity of multi-body gravitational dynamics. The comet's future trajectory, seemingly fixed by the deterministic laws of physics, actually depends on an intricate web of gravitational influences that render long-term predictions increasingly uncertain as time progresses. Small perturbations from planetary encounters, radiation pressure effects, and even the gravitational influence of asteroids accumulate over orbital periods to create exponential divergence in possible future paths. The sensitivity of orbital motion to initial conditions represents one of the most profound insights of modern dynamical astronomy, revealing how systems governed by perfectly deterministic physical laws can exhibit fundamentally unpredictable long-term behavior. For Comet 3I/Atlas, tiny uncertainties in its current position and velocity, measurement errors smaller than the width of a human hair, will amplify through repeated gravitational encounters until they encompass regions of space larger than planetary orbits. This mathematical chaos ensures that while astronomers can predict the comet's motion with high accuracy for several orbital periods, longer-term forecasts become increasingly speculative. The gravitational environment of the outer solar system creates a complex landscape of stable and unstable orbital regions that determine whether small bodies remain bound to the solar system or escape to interstellar space. The Lyapunov time, the characteristic period over which small differences in initial conditions grow to macroscopic scales, varies dramatically depending on orbital characteristics and proximity to major planets. For objects in chaotic zones near giant planets, this time can be as short as a few hundred years, while bodies in stable regions may maintain predictable motion for millions of orbital periods. Jupiter's gravitational dominance extends far beyond its immediate vicinity, creating resonant zones throughout the outer solar system where orbital periods maintain simple numerical ratios with the giant planet's 11-year cycle. These mean motion resonances can either stabilize or destabilize comet orbits depending on their specific characteristics and the direction of orbital evolution. Objects trapped in stable resonances may remain in predictable orbital configurations for geological ages, while those in unstable resonances experience rapid orbital evolution that can lead to ejection from the solar system or collision with planets. The Tisserand parameter provides a mathematical tool for understanding how gravitational encounters with Jupiter affect comet orbits while conserving certain dynamical quantities. This dimensionless number, calculated from orbital elements, remains approximately constant during distant encounters with the giant planet, allowing astronomers to identify dynamical families of comets that share common evolutionary pathways. Objects with similar Tisserand parameters often follow related orbital trajectories that reflect their shared history of gravitational interactions with the same planetary perturbers. The three-body problem involving the comet, Sun, and Jupiter admits no general analytical solution, requiring numerical integration techniques to predict future orbital evolution. These computational methods break the continuous motion into discrete time steps, calculating the instantaneous gravitational forces acting on the comet and updating its position and velocity accordingly. The accuracy of these predictions depends critically on the size of the time steps and the precision with which gravitational forces can be computed, introducing cumulative errors that eventually dominate the calculation. Chaos theory provides the mathematical framework for understanding why long-term orbital predictions become impossible despite the deterministic nature of gravitational physics. The butterfly effect, where infinitesimally small changes in initial conditions lead to dramatically different outcomes, operates in celestial mechanics just as it does in weather systems and other complex dynamical systems. For comet orbits, this sensitivity to initial conditions means that measurement uncertainties inevitably grow to overwhelm predictions on timescales much shorter than the age of the solar system. The scientific challenge of predicting Comet 3, Y/Atlas's distant future, lies in distinguishing between measurement uncertainties and genuine physical unpredictability. While improved observational precision can reduce initial condition errors and extend the horizon of reliable prediction, the exponential growth of uncertainties in chaotic systems ensures that there exists a fundamental limit beyond which no amount of observational improvement can provide meaningful forecasts. This represents a profound limitation imposed by the mathematical structure of the governing equations rather than technological constraints. Non-gravitational forces add additional complexity to orbital evolution by introducing systematic accelerations that depend on the comet's physical properties and orientation relative to the Sun. The rocket effect produced by asymmetric outgassing during active phases can significantly alter orbital elements over multiple perihelion passages. While solar radiation pressure affects the motion of particles ejected from the nucleus, these forces, while small compared to planetary gravity, can accumulate over many orbits to produce substantial changes in trajectory. Only took billions of years of stable gravitational architecture to create this zone of fundamental unpredictability. The irony emerges from the contrast between the clockwork precision of planetary motion and the chaotic uncertainty that characterizes the orbital evolution of smaller objects within the same gravitational system. The same mathematical laws that create the stable, predictable orbits of major planets generate chaotic dynamics for comets and asteroids, demonstrating how deterministic systems can produce both order and unpredictability simultaneously. Another ironic aspect of orbital uncertainty concerns the relationship between our increasing computational power and our decreasing confidence in long-term predictions. More sophisticated computer models and higher precision observations reveal the full complexity of orbital dynamics, while simultaneously demonstrating the fundamental limits of predictability in chaotic systems. Better tools for calculation paradoxically highlight the impossibility of perfect prediction rather than extending the horizon of reliable forecasting. The third irony lies in the precision with which chaos theory can predict its own limitations, providing exact mathematical expressions for how quickly uncertainties grow while offering no way to circumvent these fundamental constraints. The same mathematical framework that reveals the unpredictable nature of long-term orbital evolution can precisely calculate the rate at which predictions become meaningless, creating a kind of meta-predictability about unpredictability itself. The statistical approach to orbital evolution provides an alternative to deterministic prediction by characterizing the probability distributions of possible future states rather than attempting to identify specific trajectories. Monte Carlo simulations involving thousands of slightly different initial conditions can map out the range of possible evolutionary pathways and quantify the likelihood of various outcomes such as ejection from the solar system, collision with planets, or capture into different orbital families. Modern studies of comet orbital dynamics employ sophisticated computational techniques that can integrate equations of motion for millions of years while tracking the evolution of uncertainty regions in phase space. These calculations reveal the fractal structure of stable and unstable orbital regions, showing how tiny changes in initial conditions can determine whether objects remain in the solar system for geological ages or escape to interstellar space within a few thousand years. The concept of orbital half-life provides a statistical measure of how long populations of objects remain in particular dynamical states before evolutionary processes remove them through ejection or collision. For Jupiter family comets, this half-life ranges from tens of thousands to a few million years, reflecting the efficient dynamical evolution that operates in the giant planet region. Objects in more stable orbital configurations may persist for much longer periods, creating long-lived reservoirs of primitive material in the outer solar system. The discovery of exoplanetary systems with very different architectures from our own solar system has revealed that the specific pattern of planetary masses and orbital spacings strongly influences the chaotic properties of small body dynamics. Systems with more closely spaced giant planets or different mass ratios create different stability landscapes that affect how comets and asteroids evolve over time. The relatively wide spacing of giant planets in our solar system creates extensive regions of stable motion that allow some objects to remain bound for billions of years. As Comet 3 I/Atlas continues its journey through the gravitational labyrinth of the outer solar system, its future remains written in the probabilistic language of chaos theory rather than the deterministic equations of classical mechanics. The mathematical poetry of orbital motion gives way to the statistical prose of dynamical evolution, where individual trajectories become unknowable while statistical properties remain well-defined. In this realm beyond predictability, the comet's future paths multiply like branches of an infinite tree, each possibility equally valid according to the laws of physics, yet none knowable with certainty until the cosmic dice finally come to rest. In the vast emptiness beyond Neptune's orbit, where the sun appears as little more than a bright star against the cosmic darkness. Comet 3 I/Atlas continues its eternal journey through space with the patient persistence that characterizes all celestial motion. The ancient wanderer, having completed its spectacular passage through the inner solar system and survived the intense crucible of perihelion heating, now carries within its modified structure the accumulated memory of stellar birth, interstellar wandering, and gravitational encounters that span billions of years of cosmic time. The comet moves through this realm of perpetual twilight with the same inexorable momentum that brought it from the cold depths of interstellar space, following mathematical laws that operate with unchanged precision regardless of human observation or understanding. The nucleus, carved and sculpted by its recent encounter with solar radiation, bears the scars and modifications of thermal processing while preserving in its interior the pristine materials that formed in stellar atmospheres and molecular clouds long before our solar system existed. Each crater and valley etched into its surface tells part of the story of solar heating and sublimation, while the protective mantle of organic residues that now coats its exterior ensures that future archaeological excavation will be required to access the unmodified samples of ancient chemistry locked within. The comet has become its own museum, displaying the effects of stellar encounters in its surface topography while protecting the original exhibits in climate-controlled storage deep within its core. The trajectory that carries 3 I/Atlas away from the Sun follows the same gravitational mathematics that guided its inward journey. But now, the equations work in reverse as kinetic energy transforms back into gravitational potential energy with each passing day. The comet climbs slowly out of the Sun's gravitational well, trading speed for altitude in the cosmic landscape defined by Einstein's curved spacetime. This ascent occurs with the geological patience that characterizes all astronomical motion, measured not in human timescales but in the orbital periods of planets and the rotation periods of galactic spiral arms. As the comet recedes beyond the realm where solar heating can maintain active sublimation, it enters a dormant phase that may persist for thousands or millions of years until the next close encounter with stellar radiation. The water molecules and organic compounds that comprise its nucleus return to their primordial state of frozen suspension. preserving chemical information about the conditions that prevailed in distant stellar atmospheres and interstellar molecular clouds. This preservation occurs through the simple expedient of extreme cold, where thermal motion becomes so sluggish that chemical reactions essentially cease and molecular structures remain unchanged across geological timescales. The gravitational influence of distant planets continues to act on the comet's motion with effects that accumulate imperceptibly over vast periods of time. These perturbations, while tiny compared to the dominant solar gravity, possess the power to fundamentally alter the comet's long-term trajectory through the exponential amplification characteristic of chaotic dynamical systems. The mathematical precision of Newton's laws ensures that every gravitational interaction, no matter how small, contributes to the comet's future evolution in ways that become increasingly unpredictable as time progresses into the deep future. The particles and gases ejected during the comet's active phase continue their own independent journeys through the solar system, following orbits that gradually diverge from the parent nucleus until they become permanently separated from their source. These materials will eventually be dispersed throughout interplanetary space by radiation pressure, planetary perturbations, and solar wind interactions, contributing to the diffuse matter that fills the volume between worlds. Some fraction of this ejected material may eventually encounter planetary atmospheres, creating meteoric displays that connect the ancient chemistry of stellar nucleosynthesis to the brief flashes of light visible in terrestrial night skies. The scientific legacy of Comet 3 Y/Atlas lies not only in the direct observations made during its passage through the inner solar system, but also in the theoretical insights gained from studying its orbital dynamics and physical evolution. Each well-observed comet contributes to the growing database of information about primitive solar system materials and the processes that govern planetary formation. The isotopic ratios, organic compounds, and mineral assemblages detected in cometary nuclei provide ground truth for cosmochemical models, while constraining theories of galactic chemical evolution and stellar nucleosynthesis. The temporal perspective afforded by cometary studies spans the entire history of our galaxy, from the initial collapse of the molecular cloud that formed our solar system back through billions of years of stellar evolution and chemical enrichment. Comets serve as time machines that transport materials across vast intervals of cosmic history, preserving samples of ancient environments in the deep freeze of interstellar space. The study of these objects thus provides direct access to conditions and processes that operated long before Earth existed or life evolved in its oceans. Only took 4.5 billion years for this particular collection of atoms to assemble. Travel across the galaxy, visit our solar system, and continue onward toward whatever stellar encounters await in the cosmic future. The irony emerges from the vast scales of space and time involved in the comet's journey, where events separated by millions of years appear simultaneous from the perspective of galactic evolution, while distances measured in light years become merely the next step in an ongoing voyage that may continue for billions of years to come. Another ironic observation concerns the relationship between the comet's moment of maximum visibility and scientific interest during its brief active phase and the much longer periods of invisible dormancy that comprise the majority of its existence. Human attention focuses on the spectacular displays that occur during solar heating, yet these episodes represent a tiny fraction of the comet's total lifetime, during which it carries unchanged samples of ancient stellar chemistry through the dark spaces between worlds. The third irony lies in the comet's role as a messenger between stellar systems, carrying materials from the dying stars where it originated to whatever future stellar encounters await along its trajectory through the galaxy. The comet serves as an inadvertent ambassador from the stellar neighborhood where our solar system formed to regions of space that may be visited millions of years in the future, when different stars occupy the positions now held by familiar constellations. The mathematical laws that govern the comet's motion operate with the same fundamental consistency that characterizes all physical processes throughout the observable universe. The gravitational equations that describe its trajectory apply equally to the orbital mechanics of planets, the dynamics of galaxy clusters, and the large-scale structure of space-time itself. This universality of physical law ensures that wherever the comet's journey may lead, it will continue to follow the same mathematical principles that have guided its motion since the moment it first condensed from interstellar gas and dust. The story of Comet 3 I/Atlas represents just one chapter in the much larger narrative of cosmic evolution that encompasses stellar birth and death, galaxy formation and interaction, and the chemical enrichment of the universe through successive generations of nucleosynthesis. Comets serve as bibliographic entries in this cosmic library, preserving information about specific times and places in galactic history while participating in the ongoing circulation of matter and energy that drives the evolution of the universe as a whole. As the ancient wanderer continues its journey toward whatever destinations await among the stars, it carries with it not only the chemical memory of stellar processes and interstellar conditions, but also the accumulated gravitational influence of every object it has encountered during its passage through our solar system. These subtle modifications to its trajectory, imperceptible on human timescales, may determine whether future stellar encounters occur at distances measured in millions or billions of kilometers, potentially affecting the comet's evolution over cosmic time. The comet thus embodies the interconnected nature of cosmic evolution, where local events occurring within individual stellar systems contribute to the galactic scale processes that shape the chemical and dynamical evolution of entire regions of space. Through its wandering journey between the stars, 3 I/Atlas participates in the vast circulation of matter that connects dying stars to forming planetary systems, ensuring that the heavy elements necessary for rocky planets and biological evolution continue to spread throughout the galaxy as older generations of stars contribute their nuclear heritage to the formation of new worlds and the possibility of new forms of complexity yet to evolve in the cosmic future. The journey of Comet 3 I/Atlas draws toward its conclusion in these words. Though the ancient wanderer itself continues onward through the darkness, carrying its cargo of stellar memories toward destinations that will remain forever unknowable to human observation. The gravitational poetry that brought it from interstellar space through our solar system now guides it back toward the realm between the stars, where time moves with geological patience and distances stretch beyond the reach of even our most ambitious imaginations. In the cold silence beyond the outer planets, where sunlight fades to starlight and temperatures approach the fundamental limits imposed by quantum mechanics, the comet resumes the dormant state that has characterized the vast majority of its existence. The spectacular displays of sublimation and tail formation that marked its passage through the inner solar system fade into memory, preserved only in the photons that raced ahead at the speed of light to carry news of its visit to distant observers who may never know of its passage. The mathematical laws that governed every aspect of its orbital mechanics continue to operate with unchanged precision, demonstrating the fundamental unity that connects the smallest quantum interactions to the largest galactic motions. Gravity continues to curve space-time around massive objects. Radiation pressure continues to push microscopic particles away from stars, and the conservation laws that govern energy and momentum continue to ensure that nothing is ever truly lost in the cosmic accounting that tracks every interaction across space and time. The silence deepens as the comet recedes beyond the boundary where human instruments can detect its faint reflected light against the stellar background. Yet this invisibility does not diminish its reality or importance. It merely returns to the patient anonymity that characterizes most matter in the universe. where countless objects drift through space carrying their own histories and chemical signatures without fanfare or observation. The comet joins the vast population of wanderers that populate the spaces between stars, each following its own trajectory through the gravitational landscape that connects all matter in an intricate web of mutual influence. The isotopic ratios and molecular structures preserved within its nucleus will continue to carry information about stellar nucleosynthesis and interstellar chemistry regardless of whether any conscious beings ever examine them. The mathematical relationships that describe its motion will continue to operate according to the same principles that govern the expansion of the universe itself, demonstrating the profound unity underlying all physical phenomena from the quantum scale to the cosmic horizon. In this realm of perpetual darkness and cold, where the only illumination comes from distant stars and the faint glow of cosmic background radiation, the comet settles into rhythms measured in millions of years rather than human lifetimes. Its next encounter with stellar radiation may occur when our sun has evolved into a red giant, when the continents of Earth have drifted into unrecognizable configurations, when species yet to evolve have risen and fallen in the continuing dance of biological evolution, the atoms that comprise its nucleus, the carbon forged in stellar cores, the oxygen scattered by supernova explosions, the hydrogen that survived from the Big Bang itself, will continue their cosmic journey regardless of the specific gravitational encounters that shaped this particular chapter of their existence. These fundamental building blocks of matter have already survived billions of years of cosmic evolution and will continue their transformations through whatever stellar encounters and planetary formations await in the deep future. Time flows differently in this realm beyond observation, where orbital periods stretch across millennia and significant evolutionary changes require geological ages to manifest. The comet's motion through space continues with the persistence that characterizes all astronomical phenomena, following mathematical laws that operate independently of human awareness or understanding. The same gravitational forces that shape galaxy clusters and determine the large-scale structure of the universe guide its trajectory through three-dimensional space toward whatever cosmic appointments await along its path. The story ends not with conclusion but with continuation, as all astronomical narratives must. Recognizing that human observation represents only a brief moment in cosmic processes that began billions of years before consciousness evolved and will continue long after our species has joined the fossil record. The comet carries within its frozen heart the accumulated history of stellar generations while participating in the ongoing circulation of matter that connects past and future in the endless cycle of cosmic evolution. In the vast quietude of interstellar space, where silence stretches across light years and motion occurs at speeds that would seem glacial to human perception. Comet 3, I/Atlas, continues its ancient voyage among the stars. The darkness embraces it with the same gentle inevitability that governs all returns to equilibrium, all settling into rest, all transitions from motion to stillness that characterize the ultimate fate of energy in an expanding universe. The last photons reflected from its surface fade beyond detectability, leaving only the mathematical certainty of its continued existence and the gravitational signature of its passage through our corner of space. In this fading into cosmic anonymity, the comet demonstrates the profound patience that underlies all astronomical phenomena, where significance emerges not from immediate drama, but from participation in the slow, majestic processes that govern the evolution of matter and energy across cosmic time. Sleep now settles over this narrative as it settles over the comet itself, not as an ending, but as a return to the timeless dormancy that connects all matter to the fundamental rhythms of the universe, where motion and rest, heating and cooling, complexity and simplicity alternate in cycles too vast for human comprehension, yet governed always by the same mathematical beauty that describes the dance of atoms and galaxies alike in the infinite cosmos that surrounds and contains us all.